streaming service, right?
Yes. It might take you to a website, but you can just close it.
Okay.
We're live, I think.
Okay, if it works, that's good. Okay, I guess I can now see also people in the room as well. So let's start. Okay, there are some people on the on Zoom as well. That's good. Let me hide this one. Okay, let's get started. I was hoping to lecture in person today, but apparently they really botched the fixing of the ventilation in that room, and it doesn't seem like it's fixed. Is it fixed? Can people breathe there? It's okay?
Barely.
Barely? Really? Is it that bad? Maybe you guys should be wearing masks, but that's up to you. I mean, based on the science I know about what's going on, I think ventilation is extremely critical to long-term health of people. And it's amazing that they have not fixed this yet or provide an alternative solution. And they cannot even open the windows, apparently. So this is a security, safety, reliability problem, in my opinion, a serious one. Given the topic of the lecture, it's well-fitting. As you can see, there are these failures that happen, even though a week ago, there was a serious complaint filed. So we're going to file that complaint again, and we'll see what happens. Okay, I guess let's get started. We're going to talk about RowHammer, and we're going to finish this topic, but I would like people to think about it and brainstorm a little bit, because this is an important topic, and we need solutions to this sort of problems. You may think that, oh, we're not able to even solve things that we know very well, like ventilation. But yeah, that's a matter of will and capability and importance you assign. Here, we don't know how to solve it well. Here, the difference here is there's a problem at hand in memory technology scaling, and no one has developed solutions, but people can develop new solutions, basically. So if you have ideas, you can actually impact the world. So let's start. I'm going to go through some overview slides. So we've discussed RowHammer, so everybody knows what it is. I'm not going to talk about it more. There are papers, some of which we covered. There are surveys that are written on the topic. It is actually a good one that introduces you to a lot of RowHammer research very quickly. And we also discussed that solution requires intelligent controllers to some level. That intelligent controller may be sitting in the DRAM chip, in the memory controller. We're going to talk about that. And we were covering RowHammer more recently as well, about 10 years after it was discovered. We were looking at research that was done in 2020 and 2022. And we talk about revisiting RowHammer. This work is going to be one of their papers in your homework. Shows that it's becoming much worse. We talked about industry adopted solutions not working because they're not secure enough, let's say. And then we talked about infrastructures to understand many of these issues, the soft MC infrastructure, and we mentioned that. And we also showed that using these infrastructures, you can show that you can basically reverse engineer all of the solutions that are deployed and learn a lot about the RowHammer problem. And then we talked about like discovering new characteristics of RowHammer, again, using such infrastructures. Because these infrastructures enable you to examine temperature effects on RowHammer, aggressor row active time, different physical variations. And there's a lot more to examine, like the effect of aging on RowHammer. This is actually a serious issue that needs to be understood very well. As DRAM chips age, let's say you're using a DRAM chip that's 5 years old, what happens to the reliability characteristics, specifically RowHammer characteristics? They become more vulnerable to RowHammer? I believe they do, but there's little data, if any, on this topic. And again, you may say, okay, who has 5-year-old DRAM chips? I think I would argue that a lot of us use 5-year-old DRAM chips. A lot of the cloud infrastructures in the world is dependent on 5-year-old DRAM chips. And in fact, some things that we send far away, like into the space, are even more than 5 years old. They use chips that are much, much older, right? Because it's not easy to replace them in the field. In fact, it's not possible to replace them in the field in many, many cases. So it's good to think about, again, these unforeseen consequences of how we use computing systems. So there's a lot to understand in RowHammer. And this is a talk that Giray delivered. So if you're interested in this, he may actually deliver a longer lecture on this later on, but this is from last year's class. You can see lecture 16, fall 2021. You can learn more. Now, we also talked about more RowHammer analysis, which I'm not going to go into details. We're going to talk about actually voltage a little bit in the next lecture on latency. But again, Giray, you can talk to Giray about it. There's another talk Giray delivered recently in the DSN conference talking about wordline voltage effects on RowHammer. And we discussed this briefly, saying that it does have an effect. It reduces the RowHammer vulnerability if you reduce the wordline voltage. But unfortunately, it has also effects on other things. So overall, there is a reduction in RowHammer vulnerability, but this is not the complete solution to the problem. But it's important to understand these effects clearly. Okay, any questions so far? Feel free to interact. Okay, there's one question. Please go ahead. I think you can press the button, then I can hear you much better.
Okay, what is wordline voltage?
Oh, okay. So wordline, remember the wordline is the row. You have a row of cells, and wordline is the wire that controls access to that row of cells. And there's when you want to activate the row of cells, access that row of cells, which is essentially a hammer, if you remember, you need to apply high voltage to that wordline, to that wire, essentially. And the amount of voltage that you apply determines how much vulnerability you cause to the adjacent word lines or adjacent rows. So that's the amount. Essentially, it's the amount of voltage that you apply to the word line when you activate the word line. Does that make sense?
Yeah, but then this word line doesn't mean one word, right? It's just called word line.
Exactly. Yeah, it's essentially the wire used to activate the entire row, but people call it word line.
Okay, clear.
Okay, great. Any other questions? Okay, so let's move on then. Let's talk about some solutions. And this is going to be even more important as we discussed into the future. So what are the solutions that we want? I'm going to talk about this work. Again, Giray had driven on RowHammer. It's essentially one solution that introduces an intelligent memory controller. But before that, I will cover some broad solution directions. And this work was more recently selected as one of the 4 finalists of top hardware security papers in 2021 by Intel, as you can see over there. Okay, so let's cover the solution directions a little bit more. We've covered it in the last lecture, but the first one, as we discussed, is a tough one. How do you design more robust DRAM chips and or use error correcting codes? These are very costly solutions in general. They require either new materials or very expensive error correcting codes. As a result, there are no, let's say, realistic solutions in the field about this. There are papers written about, especially the robust DRAM chips part. There are papers written about error correcting codes, but they usually show that your error correcting code needs to be extremely expensive to correct all of the RowHammer bit flips, as we discussed last week. So I'm going to not talk about these solutions much. Increasing the refresh rate across the board, again, it's not a great solution, as we discussed, because as you increase the refresh rate, you reduce the vulnerability, but this has a lot of problems, as we will also discuss in the later part of today's lecture. Physical isolation is a solution that could be employed at the software level, operating system level, for example. Why not isolate victim rows from aggressor rows? In the extreme case, why not have spacing between all rows in memory and don't allocate data into the isolation rows in memory so that you don't disturb any, let's say, data that you may care about potentially. So clearly, this physical isolation has a lot of overhead, right? Because you need to have large enough distance between the rows, and that distance is not easy to maintain. It's not just one row, usually. It's sometimes 2 rows, 3 rows, sometimes 4 rows today. So that's why this solution becomes very expensive as well. Although this could be a potential software solution. There are other software solutions that could be employed using reactive refresh, proactive throttling, but usually these are hardware solutions, as we will discuss. Reactive refresh is a more realistic solution today. Basically, detect aggressor rows somehow and refresh potential victim rows so that potential victim rows don't lose their data. And as we discussed, it's the access counter-based solution from last week. And there are many approaches that are developed recently in reactive refresh. Probabilistic adjacent row activation solution that we discussed in a bit more detail last week is actually a reactive refresh solution, if you remember. Whenever you activate or close a row, you flip a coin, and based on a probability, you refresh adjacent rows. So it's not trying to detect aggressor rows, but it's trying to guess that something bad is happening every time you activate a row, and probabilistically, it tries to refresh these adjacent victim rows. And one issue with these solutions is clearly the hardware cost for detection. Para doesn't do that because it doesn't detect them. But the other issue is you need to know the physical adjacency of victim rows and aggressor rows. And this requires knowledge about the DRAM chip internals. We're going to talk about that a little bit more. Proactive throttling is a solution that RowHammer employs. The idea is, again, detect recently activated or rapidly activated rows that are potential hammers, and throttle the accesses to those rows so that you don't activate them more than a rate or frequency. Okay, we're going to talk about that. I think all of these solutions are quite interesting, but they all cover a trade-off space in terms of cost, power, performance, and complexity. So as far as I know, there's no perfect solution to RowHammer today that is good on all aspects. For example, probabilistic adjacent row activation is great in terms of cost. It's very low cost, no storage overhead, very low complexity. But unfortunately, its performance and power overheads increase as RowHammer vulnerability becomes worse. So we're going to talk about that also. I must mention there's another solution approach over here, which is moving the rows. So whenever you access some rows a lot, why not move the victim rows or the aggressor rows somewhere else? This is called row swapping or row movement, let's say. Row copy in general. And if you can do this efficiently, this could potentially be a solution direction also. I think these slides need to be updated after this lecture, talking about, let's say, row swapping as a potential solution approach. But it's always good to keep in mind the cost of swapping a row, because whenever you need to move the row somewhere else, you need to either have space. There are two things. You need to have space to move the row. If your memory is empty, there's some empty space, that's great. But if there's no empty space, you need to swap the row that you're whose physical location that you're going to occupy by moving either the aggressor row or the victim row. And then there's the cost of row movement or row swapping, which is significant because we're talking about 8 kilobytes of data, right? You need to move 8 kilobytes of data from one location to another location in memory. And that may be very costly unless you have specific mechanisms implemented in memory to facilitate that to be quick. As we discussed, as Juan discussed in processing using memory lectures, a row clone approach can be actually useful for this purpose. Okay, any questions on this? This is a broad overview of the solution space. Maybe someone has a completely different solution space or solution direction. That's always welcome also, right? Here I claim to cover the entire solution space, but maybe there's something else that's missing that people have not examined, and that's good to think about into the future. Okay, so I'll move on. So let me discuss what the RowHammer work covers. I'm not going to spend a whole lot of time, but I'm going to give you the challenges that this work is trying to solve, and also challenges in supporting what we're trying to do. So one challenge we talked about last time is scalability. As DRAM chips become denser, RowHammer vulnerability becomes worse. The number of activations to induce bit flips reduces significantly, as we discussed. And the second challenge is compatibility. ideally, we do not want to have any information from the DRAM chip because we may not have that information. As we discussed, the row accesses that memory controller generates, the addresses that the memory controller sees, are not necessarily physically adjacent to each other in DRAM. The memory controller doesn't know the physical adjacency of the rows. So it essentially requires more information about the DRAM chips to expose which rows are physically adjacent, which is not done today for various reasons, as we will discuss. So we want to remain compatible with commodity DRAM chips without changing them. You could argue that, okay, this is a short-term concern. It is true. It is a shorter-term concern, hopefully. But this is a very realistic, real-world concern today that people do not want to provide information about the internals of their DRAM chips because they think they lose competitive advantage if they do provide that information. Yeah, we'll talk about that mindset later on, but that's what we would like to do. So what happens to these solutions when you worsen the RowHammer vulnerability? For example, increasing the refresh rate clearly is not good, as we discussed, right? Your refreshes increase a lot, and that's a huge performance energy overhead. Increasing as RowHammer vulnerability becomes worse, you may need to increase the number of rows that are used for isolation, so you're wasting even more memory space. Reactive refresh, you need to refresh more frequently and refresh more rows because both the number of victim rows increases as well as the RowHammer threshold to induce bit flips reduces. And proactive throttling, you need to more aggressively throttle row activations because the RowHammer threshold required to induce bit flips also reduces. So all of these solutions become worse, essentially, as RowHammer vulnerability becomes worse. Yeah, so all of these solutions face a scalability challenge. Let's talk about the compatibility challenge. So if you look at the compatibility challenge, this is a more clear depiction of what we discussed last time. Applications see virtual memory addresses, system converts them to physical memory addresses using the memory management unit, and memory controller converts them to DRAM bus addresses by doing some things to the memory addresses, as we will discuss in later lectures, so that it can randomize, for example, the accesses, the address to bank mapping, and that helps with performance. But these are all visible to the processor because memory controller sits within the processor. Now, once you go to the DRAM chip, the in-DRAM mapping of addresses, this is the real physical mapping. Where do two physical rows, where are two physical rows with respect to each other inside the DRAM array, for example? Where are two physical columns with respect to each other inside the DRAM array? This mapping is internal to the DRAM chip. No one above the DRAM chip knows this, essentially. Memory controller doesn't have this information. And this happens for multiple reasons, actually. One is internally by remapping some rows and remapping some columns, or having some function to determine the address of the rows and the columns. The DRAM manufacturers can provide better density. For example, if you want to read four bits from a word in DRAM, it's better to space out those 4 bits in terms of the columns, as opposed to having them consecutive in consecutive, let's say, column or bit lines in DRAM. Because if these bit lines that you're reading are too close to each other, you're essentially causing some reliability issues. You're activating many bit lines that are very close to each other concurrently. But if you space them out, then these bit lines map to different physical locations clearly, but logically, they're the same 4 bits or they're consecutive 4 bits that you're reading. So this is an example of why DRAM manufacturers optimize the mapping of, let's say, columns. There are similar examples for rows as well. And also, the DRAM manufacturers, as we discussed, figure out faulty rows. They do a lot of testing, and some rows are faulty, some columns are faulty. And they don't throw out the chip because there's a faulty row. There are some rows that are used just for remapping, correcting those faults. So, for example, row 55 has a stuck at fault, meaning a bit is stuck at 1, or multiple stuck at faults. They map row 55 to a spare row. And the spare row may be physically completely in a separate, even subarray. It could be in some other part of the subarray, but it could also be in separate subarray. That's what happens in DRAM today. Similarly, you can remap columns. If there's a faulty bit in a column, in a bit line, you can remap that bit line to some other location. And this remapping function clearly changes the physical basically it affects the physical adjacency of different addresses that are generated by the memory controller. And these are real, these are done. The row remapping and column remapping is done a lot. And these are very basic techniques for reliability, basically. If a row is not working, remap it to some other row that you know is working, essentially. Okay, but basically, the reason why DRAM manufacturers seem concerned about not exposing what they do internally is because this gives insight into their chip design and manufacturing quality. And this is clearly critical business problems with DRAM. So if someone has insights into how you exactly do your remapping inside your chip, may give indications of how bad, let's say, the problems, reliability problems are with your chip. And as a result, this may affect business decisions now, right? Someone can say, oh, okay, I see that these people are doing a lot of internal remapping. Maybe their chips are not as good, so I'm not going to buy many chips from them, right? So this is clearly a very clear business concern. It's not a research concern, clearly, but it's a business concern that people may have if they're selling these chips. So that's one of the reasons why manufacturers are very reluctant to expose this information. And that's why in DRAM mapping is proprietary information today. Now, we could question that. We could also discuss like how to expose this information in a way that doesn't reveal a whole lot about the internal reliability characteristics. We argue that in a later paper that I will briefly mention, but we're not going to talk about. So there are ways to reveal some of this information without really exposing a whole lot, in my opinion. But that's more research currently. Okay, so basically, in DRAM mapping is proprietary information, and this clearly affects the solutions, right? If a solution relies on identifying victim rows or isolation rows, then you have to know this mapping if you want to be complete and completely secure in your solution, because clearly victim rows are rows that are physically adjacent to aggressor rows, and isolation rows are also rows that are physically adjacent to aggressor rows. So these two solutions essentially require some proprietary information to be exposed. And if that's not what you want, then these two solutions essentially do not work perfectly. That's the unfortunate fact of life. You could argue that, yes, you can reverse engineer DRAM chips to find all possible victim rows. And I think that is true to some extent. That's doable, but that requires a lot of effort. And that effort is very DRAM chip specific also. So for every single DRAM chip, you need to figure out this information. And that's a lot of testing cost for just reverse engineering. So it is possible to make these solutions work with a lot of reverse engineering, but it becomes very costly. So this is the trade-off right now, right? You have a cost trade-off to make the solution work. So there's actually a trade-off in security also, because if you don't make this solution work, if you don't know all of the victim rows and isolation rows perfectly, then your security gets compromised. I'm assuming that we don't want that. We don't want compromised security. But if you go back to this picture that I showed you earlier, which covers the trade-off space, there's cost, power, performance, complexity. There's also security over here. It's like security guarantees. How strong are your security guarantees? You can always make a solution less costly by trading off some security, by saying, okay, I'm 95% good. But is that what we want? Is a very serious question, because if you're 95% good, there will be someone in the world who will figure out that 5% bad part that you don't cover. Okay. Any questions? Yes, please. Another question.
I was wondering if remapping is really useful for faulty rows. Is it can also help with this RowHammer, like when we know we access this row that frequently, and we can remap it pretty forwardly?
Yeah. So that's a good question. That's one of the solution directions actually that I mentioned, which is row swapping or row remapping. Yes, it could be useful, certainly. So if you can, and this could be done by the memory controller again. But the question, of course, it becomes, where do you remap? Like what is in that location that you remap the row in? Because if there's some useful data in that location, then you'll need to swap the row with that row. And also the cost of the remapping, right? Because you need to move the data from the aggressor row or the victim row to the place that you're remapping those rows to.
Is it possible to do it in the middle way? Like when we are running the program, we know, okay, this row, we are accessing it a lot. then we just divide the access time, and in the middle we do this remapping.
Yeah, there are solutions that are proposed. I'm going to mention some papers later on that do that sort of remapping. I like your thinking. Certainly, it needs to be done dynamically for RowHammer.
Okay.
Okay, great. Any other questions or solution directions? Okay, so I'll move on. Okay, so the goal of this work is to prevent RowHammer efficiently and scalably without knowledge of or modifications to DRAM internals. So actually, I should say that the remapping also it can achieve this. If you remap the aggressor row, not the victim rows, you don't need to know the victim rows. So potentially you can do that without modification to DRAM internals. But we have a different solution. Let me talk about that. And the idea here is very simple. The idea is to selectively throttle memory accesses that may potentially cause RowHammer bit flips. So let's take a look at the idea. So RowHammer access pattern hammers row A. The block hammer detects a RowHammer attack using area efficient Bloom filters. How many people know about Bloom filters here? Anyone? How many? Okay, some people. Maybe people who've taken DDCA. How many people do not know about Bloom filters? Okay, so I'm not going to talk about Bloom filters right now, but when we talk about refresh, I'm going to introduce them. But let me give you the basic idea. So Bloom filter is essentially a data structure. It could be implemented in hardware or software. And the idea is to approximately represent set membership. So you have a bit vector. Think about it as a bit vector. And you represent the presence of an element in a set by setting some bits in this bit vector. And then you check whether an element is present in that set by checking some bits in that bit vector. I'm going to show you a more detailed example when we cover refresh. But this is an approximate way of representing whether a row, for example, is frequently accessed. So you have the set of all rows represented by a bit vector. Its bit vector is limited size and much smaller than the set of all possible rows. And then you detect some rows that are accessed frequently, and you set some bits based on the addresses of those rows. And these bits tell you essentially those rows are present, meaning they are accessed frequently. Now, when you give the address of the same row that you inserted into the Bloom filter, and when you check it again, the Bloom filter says, oh, okay, I've seen this, this was inserted, so I have this in my set. So basically, this Bloom filter can enable you to keep track of which rows are frequently accessed or accessed too much, let's say. We're going to see this in more detail when we talk about something else later on. But as long as you have this key idea, now you can imagine how area efficient this could be, right? Basically, whenever you insert something into this Bloom filter, you always can get that something is inserted. But because this is approximate, sometimes this Bloom filter tells you that you inserted something even though you have never inserted that address, because there's some aliasing going on. It's not really perfectly keeping track of what you have inserted. It can basically overestimate what you have inserted, but it can never underestimate what you have inserted. If you inserted a row, you will always get the answer, you've inserted this row. But if you did not insert a row, sometimes you may get the answer, yes, oh, you have inserted this row. So that's a false positive. So this Bloom filter structure can be very area efficient, and that's why BlockHammer uses it. BlockHammer uses it in a more sophisticated way than I just described, because it uses counting Bloom filters, because it requires some counting as well, and it uses 2 Bloom filters. I'm not going to talk about that. You can ask Giray about the details of it and grill him with a lot of questions about the design if you're interested. Right, Giray?
Yes.
Okay, good. And the source code is all open source, so you can also play with the source code if you're interested. But basically, after you figure out which accesses which rows are frequently accessed, you can the memory controller can say, okay, I know I'm getting a row address. Let me check if it's in my Bloom filter. If it's in my Bloom filter, I know that this row is frequently accessed, so I'm not going to access this row for some time. That's the idea of selective throttling. And of course, this time, that some time that I said needs to be carefully determined, because if you actually don't determine that time carefully, you may actually run into bit flips. But the paper discusses how to determine it such that bit flips do not occur. That's the idea, right? So the idea is actually at a high level, relatively simple. Of course, implementation always requires work, and you can read the paper for more detail. Now, the benefit of this is you don't need to know victim rows, right? You're just looking at the aggressor row addresses and trying to figure out which aggressor row addresses are frequently accessed. And if something is too frequently accessed, you're saying, stop, I'm not going to access it until I know that it's safe to do so. Clearly, this has an impact on performance also, right? Because you don't want to do that for all the rows, as we discussed in the last lecture also. And it turns out RowHammer can detect the attacks relatively well. I'm going to mention that. And it can also inform the system software about the attack. So if a thread is frequently accessing some row, RowHammer can figure that out and say, okay, system software, this thread is, let's say, doing too many aggressor row accesses. So do something about it. Figure out what's going on, basically. Clearly, at the memory control level, you may not have that information. So the upside is this requires no proprietary info modifications to DRAM chips. And as we will see, it scales reasonably well with RowHammer vulnerability, but maybe not too well as the RowHammer vulnerability becomes really bad. And Giray can tell you more about that also. So let me give you the overview of the approach. So there are two components to this. One is row blocker. It tracks row activation rates using these Bloom filters, whose basic idea I gave you. It blacklists rows that are activated at a high rate. And it essentially throttles activations targeting a blacklisted row, as I discussed. And the key invariant to make sure of is that no row should be activated at a high enough rate to induce bit flips. Now, this is really important. The question is, what is a high enough rate to induce bit flips? This goes back to the testing that we discussed, right? You need to figure out the RowHammer threshold of a DRAM chip. So RowHammer uses that information. This is the RowHammer threshold of a DRAM chip. Somebody needs to determine it. Again, it could be in the field. It could be provided by the DRAM manufacturer. But it's essentially everything that we have discussed in terms of testing chips, like what we have been doing for years, that needs to be done to figure out for every chip what is the RowHammer threshold. Okay, the second component is attack throttler. Here, you can actually identify a thread that perform RowHammer attack, or multiple threads if there are multiple threads. And you basically reduce the memory bandwidth usage of identified threads. If a thread is more likely to be performing a RowHammer attack, you provide less bandwidth at the memory control level to that thread, saying, okay, you're doing something fishy from RowHammer perspective. You're not getting a lot of memory access rate from me. We're going to talk about memory quality of service later on. So this resembles some of the memory quality of service mechanisms. And it turns out doing so greatly reduces the performance degradation and energy wastage a RowHammer attack cause on a system. So here, I think there's also another interesting trade-off here. So, okay, row blocker ensures that you don't activate a row at a high enough rate. Now, attack throttler goes another step forward and says, I'm going to improve system performance, even though there may be a RowHammer attack in the system. So it's good to think about that. Okay, so let's say I'm not going to go through the details of this, as I mentioned, but there needs to be some logic to do the blacklisting, which consists of essentially Bloom filters. These are Bloom filter examples, counting Bloom filters. And then there needs to be some logic to do the delaying in the row blocker. And again, all of these need to be carefully designed. More details, please ask Giray. And again, he may have a lecture on this later on. Attack throttler, I will mention this a little bit because I think this is important to think about going into the future also. If something bad is happening in the system and if you have a detection mechanism, it's good to design the entire system hierarchy so that you can respond to this at a higher software level also. That's the idea over here. As I said, a RowHammer attack clearly keeps activating blacklisted rows. And this work introduces what is called the RowHammer likelihood index. And this is defined as the number of activations that target blacklisted rows, because you know which rows are blacklisted. These are in the Bloom filter. And if you activate them again, you basically increase this count, RowHammer likelihood index, and it's normalized to a maximum possible activation count within a refresh interval. And if this number is closer to 0, that means that the application is not activating blacklisted rows, right? That means that it's probably not a RowHammer attack. That's good, assuming your Bloom filters are working, which they should if you design them well. On the other hand, if this number is very high, that means that the application is a RowHammer attack. We normalize it so the number can be maximum 1.0. Essentially, here, the blacklisted row activation count is very close to the RowHammer threshold. And that's the idea over here. This metric can enable you to distinguish between a benign application and a RowHammer attack. Now, as I said, your Bloom filters need to be designed carefully for this to work. If your Bloom filters give a lot of false positives, meaning even though an application is not activating a blacklisted row, the Bloom filter says, oh, you are activating a blacklisted row because you're having aliasing in your Bloom filters, then this metric also breaks down. Okay, so you need to size your Bloom filter as well. And we will get back to that again. And the attack throttler makes use of this RHLI information and applies a smaller quota to the in-flight request count of a thread. So if a thread has a high RowHammer likelihood index, it can send fewer requests to the memory system, essentially. That's the idea, basically. So if you're detected as a RowHammer attack, ideally no request to the memory system should be allowed, and you get informed to the system software. Otherwise, if you're a benign application, no code applied. There may be some gray areas over here as you approach a RowHammer likelihood index that's closer to a RowHammer attack. So that's the idea, basically. This reduces the memory bandwidth consumption of RowHammer attack and enables a larger memory bandwidth for, hopefully, applications that are identified as benign. And I already said this. Okay, any questions? Okay, so let's take a look at the performance and energy impact using a simulation of this work, because this requires hardware changes to the memory controller. It's a pure memory controller based approach, as we discussed. So it needs to be simulated. And this is done via simulation using Ramulator, which was mentioned last time. But we'll talk about Ramulator later on also. In fact, you're going to do an assignment using one of those later on. But this work studies a lot of metrics: system throughput, job turnaround time, unfairness across different applications, and DRAM energy consumption. I'm not going to go through all of these details. You can imagine what these are clearly, and you're going to read the paper at some point as well. But basically, if you look at this, the red bars are BlockHammer bars, and they're almost always very close to the baseline. Baseline is 1.00. This is normalized to the baseline, which is no RowHammer solution employed in the system. Ideally, a RowHammer solution should not induce any performance overheads or energy overheads or any unfairness in the system, right? And BlockHammer is achieving that. And these other solutions are also kind of achieving that, but not all of them, as you can see, right? Para, probabilistic adjacent row activation, has some slowdown. I believe the threshold over here is 32K. Is that right, Giray?
Yes, that's true.
Okay, so the RowHammer threshold is actually relatively high. We will see how these solutions fare as RowHammer's threshold also reduces. And RowHammer threshold is, remember, the number of activations you need to do to induce a bit flip. Okay, so the takeaway is there's very low performance energy overheads with this solution. And if there's a RowHammer attack present, this is where BlockHammer shines, because no other solution throttles the attacking thread. Whereas here, fundamentally, BlockHammer throttles the attacking thread, and as a result, it improves performance of non-benign applications, as well as reduces DRAM energy consumption overall, because you're not wasting energy on activating rows due to a RowHammer attack. And I think this is the sign of a good solution. In fact, all solutions should have this property going into the future, detecting the RowHammer attack and not allowing it to continue to sap system resources like performance, energy, unfairness, etc. Okay, so I'll throw you another graph over here. This basically shows the scalability with the RowHammer vulnerability. Here, Giray varies the RowHammer threshold from 32K to 1K. And we look at different solutions, 4 of them in this particular case, how they scale. We've kind of seen this last time in some other paper, revisiting RowHammer paper. We've seen that Para doesn't do well. Here we cap at 1K, as you can see. So Para is not very good, a probabilistic adjacent row activation. Other solutions are okay, as you can see, they don't lose performance. So BlockHammer is as good as those other state-of-the-art solutions, basically. Its performance energy overheads are negligible. But when a RowHammer attack is present, again, throttling those attacks lead to much higher performance as well as much lower energy consumption than the state-of-the-art mechanisms. Okay, and Giray can tell you more. Hardware overhead is also important. The paper covers a lot of hardware overheads of different mechanisms, as you can see over here, including para. You can see that the good thing about para is it's very low cost, low energy, low power, very low. There's no area cost essentially, whereas all of the other solutions have some sort of area cost, and some of them are quite large SRAMs and content addressable memories. And you can see more details in the paper clearly. But it turns out RowHammer is like competitive with state-of-the-art mechanisms. Different mechanisms have different trade-offs, but we're not going to that. Now, the scalability of RowHammer is better compared to prior mechanisms or comparable mechanisms, let's say. So you can see that prior mechanisms, as you reduce the RowHammer threshold from 32K to 1K, their hardware overheads, you can see in red over here, increases more than the hardware overhead of RowHammer. So RowHammer is more scalable than these prior solutions at the time it was evaluated. There are some other new solutions that are out there that are not evaluated against, of course. Yeah, do you have any comments?
No, I think you covered it really well.
Okay. Okay. So this is still a concern, though. Going into the future, how do you make things low complexity is a big issue. So I like the para over here, as we discussed last time, because the complexity is very low. But the problem is that it's performance energy overheads. So the question is, can you get the complexity and cost of para without the large performance and energy overheads of the other solutions? Because RowHammer is still large. And I believe Giray would agree with that also.
Yes, that's true.
Okay, good. Okay, but it's still a good solution to discuss. So these are the key results. I think I've already mentioned these, that there's a security proof in the paper. Whenever you provide a solution to a security problem, it's important to have a security proof. But I'm not going to cover that clearly. And it's important to address many-sided attacks today. And the paper, one of the reasons I'm going to assign this paper is it covers many different mechanisms. So it basically creates a terminology in terms of how these different mechanisms should be evaluated. Are they comprehensive in their protection? Like, are there holes, security holes, or are they comprehensive? And some papers actually do not fully provide security. Are they compatible with commodity DRAM chips without modifications? Do they scale well with RowHammer vulnerability? You can see that many solutions have red over here. So many solutions have a scalability problem. And do they provide deterministic or probabilistic protection? That's also important. At least the mechanism should be deterministic. So para fundamentally is probabilistic because the mechanisms that it employs are probabilistic, right? Whereas RowHammer is deterministic because the mechanisms that it employs are deterministically determining which rows are frequently accessed. Okay, now it's good to also say, critique this a little bit. So going back to this picture over here ends at 1K, right? So what happens when you reduce this number to 64 or 128 activations? Clearly, we know what happens with para because I showed you those results in the prior lecture. But I think the results are also not good for other mechanisms, including RowHammer. Is that correct, Giray?
Yes, that's correct, unfortunately.
Yeah, so basically, as you scale as the RowHammer vulnerability becomes worse, like 256 activations induce a bit flip, all of these mechanisms become bad in terms of performance. And bad depends on, of course, your tolerance to performance loss. But yeah, I think you can look at Giray's recent paper, which he may present as an example. Or maybe he'll present new data that's not published. Okay. So this is the challenge, basically. There's still work to be done in this area. And there are actually many more ideas, as I will show you in a little bit, that we're not going to be able to cover. But they all fall into the different solution approaches that we mentioned. Okay, there's more in the work that talks about, like, how do you design area-efficient bloom filters? That's important. We talked about the security proof, many-sided attacks, and also system integration. And hardware complexity analysis, and that's all in the paper. So when you write a paper, it's important to cover all of these issues. I think I've mentioned all of this. This is just a summary. And the good news is this is open source with 6 state-of-the-art mechanisms. Now, this semester, we don't have a lab on RowHammer, but if someone takes it next semester, we may actually have a lab on RowHammer where you experiment with some of these mechanisms, but we'll see that. But people can actually develop mechanisms based on the open source. And if you want to learn more, Giray has a lecture on BlockHammer that you can watch or just talk to. Any questions? Comments? I cannot see all hands, but so if you're in the back, you have to maybe wave like this. Okay. Okay, no questions or comments. So I just wanted to cover one solution, and this is a solution that shows what I mean by intelligent controls. Now your control is becoming even more intelligent, right? It's keeping track of which rows are activated frequently. It's doing that using hardware-efficient balloon filters. It's also keeping track of which threads are more likely to be a RowHammer attack. It's informing the system software. So now your control is actually much more intelligent. And I think this is a good direction to go into the future, as we discussed in the last lecture also. Now, let me cover some works that have happened in 2020 and 2022, but I'm not going to go into any sort of detail because otherwise we'd be spending the entire course on RowHammer. But you can see that there's a lot of work going on RowHammer. This is a top architecture and systems and security conference have a lot of papers on RowHammer. For example, Graphene was a solution that was proposed concurrently with BlockHammer. It's good to look at that. It basically uses an algorithm called frequent item counting using Misra-Gree's algorithm in the memory controller to detect frequently activated rows. BlockHammer takes a different approach. It uses balloon filters. So you can see that people are using different algorithms and data structures to detect which rows are frequently accessed. And then there are also attack papers. So there's both solution papers as well as attack papers. This is a top security conference, IEEE Security and Privacy. You can see that there's a session on RowHammer. I'm not going to cover that clearly. There's a lot. There are people who are looking at attacks on neural networks. Even operating systems conferences have papers on RowHammer talking about like how do we actually rethink the system. There are actually really interesting works that build on trespass, for example. Smash is one example that essentially does RowHammer attacks using JavaScript. There's more. You can see IEEE Security Privacy also has a lot of interesting papers, both solution and attack papers. Blacksmith is another work that builds on trespass that we discussed last time, that essentially does RowHammer automatically in state-of-the-art chips. Basically, it induces bit flips automatically in state-of-the-art chips. It's an automatic tool that you can download. I will mention the last one also. This is also interesting. But this work, Deep Steel, shows that you have a neural network and you have some model and you have some weights in the model. Essentially, using RowHammer to cause bit flips, you can figure out what are the weights employed in your neural network. This is actually a really interesting work, I think. We don't have time to go over the details of any of these works clearly, but if you're interested, you can cover them. You can look at them. But you can see that a bit flip can actually lead to data corruption that leads to taking over the system, but also it can lead to confidentiality issues, privacy issues, where you are not supposed to know the weights employed in your neural network because it may be very private information, but you can actually steal that information using RowHammer. This is like you were asking the question about row remapping. This is a solution that was proposed to swap rows by basically moving the aggressors somewhere else after detecting them. It's interesting, but it has overheads in terms of, because whenever you need to move data between memory banks, it causes some overhead. There are other works that, again, I'm not going to talk about, but you can see actually people are quite doing a lot of interesting research on RowHammer. For example, this work from Microsoft that was presented at International Reliability Physics Symposium argues we should not hide information that's inside the DRAM chips. This is similar to what I'm going to mention also. We also argue similarly, because it really hurts some of the system level things that you can do, like RowHammer solutions. This is an attack that was developed by Google. Looks like you're having trouble in with the air in the room. We'll take a break, hopefully soon. This is an attack that was introduced by Google that basically shows that you can hammer one row a lot, and then you can hammer another row little, and you can still cause RowHammer bit flips. So this is actually interesting. Another type of attack that was not demonstrated before. And there's more work that you can see. You can recover private keys, as we discussed, using RowHammer. There are many works that recover private keys in different ways. And these are more solution directed, solution directed, or solution papers also exist in top conferences. I'm showing you all of this because it's really interesting that people are trying to understand the problem, solve the problem, show the security aspects. I'm not covering clearly all of the work because there are also device level works that try to explain or solve the problem, but I don't have all of that coverage at this point, at least here in these slides. So Guy can tell you a little bit more about this here. I'm going to mention this later when we talk about refresh. But if you actually reduce the refresh latency or improve the parallelism of refresh, you can help the RowHammer solutions in real DRAM chips. I will mention this work that we have released recently. This work was led by my PhD student Minesh Patel, who graduated very recently from ETH. He actually won the doctoral dissertation award, William Carter Award, from the Dependable Systems and Networks Conference. But his last work essentially makes a case for more transparency in the DRAM system. Let's expose more in the DRAM system so that we can provide better reliability in the entire system, so including the software stack. Again, I don't have time to go over this, but these works provide solution directions to general reliability problems as well. I will cover one work that was released recently. Again, another PhD student who got his PhD defended recently, Hassan. And this work takes a different approach. Can we change the DRAM interface a little bit, slightly, so that we can solve RowHammer and other issues more easily? And the idea here is self-managing DRAM. And the general idea is to enable a DRAM to autonomously perform maintenance operations. So you can think of refresh as a maintenance operation. You're refreshing DRAM once in a while, right? We're going to talk about that a lot more in the second part of this lecture. You can think of RowHammer as another maintenance operation. RowHammer protection is a maintenance operation that the DRAM chip needs to do whenever there might be something bad going on that could induce RowHammer bit flip. So these are maintenance operations. And the idea in this, what happens in today's systems is that a DRAM chip doesn't have any breathing room. DRAM chip basically takes commands from the memory controller and has to respond by some time that's dictated by the DRAM datasheet. So the interface that we have designed is very, very rigid today. Memory controller sends an activate command. DRAM chip has to do the activate by some amount of time. And the memory controller says, by this amount of time, I assume the activate to be complete, so I can send the other command, assuming that activate is complete. So it's very rigid interface, which means that DRAM chips cannot do much by themselves. So they cannot even do refresh by themselves. The memory controller needs to instruct them to do the refresh by sending a refresh command. So that's very rigid. And this allows very little room for the DRAM manufacturers to, let's say, provide solutions to refresh, RowHammer, and other things that are maintenance operations. And the idea in this work is to provide some breathing room. Basically, enable the DRAM chip to say, okay, I cannot service this right now because I'm doing something really important. So please send it to me again. That's the idea, basically. Make the interface less rigid. And I've just said this over here. Prevent the memory controller from accessing some DRAM regions that are under maintenance by rejecting row activation commands. And if you look at the implementation, this requires the DRAM chip to have a mechanism to tell the memory controller, I don't acknowledge what you sent to me. Basically, I'm going to ignore your activation request. And the memory controller then needs to do something about it, of course, right? It knows that activation will not be serviced for some time. And if you actually leverage the activity to the ability to reject an activation, you can implement a maintenance operation completely within a DRAM chip, because the DRAM chip can do that maintenance operation for the amount of time it requires without requiring the memory controller to be involved in that operation. That's the idea here. So what are the maintenance operations? We're going to talk a lot about DRAM refresh, but clearly periodic refresh exists in DRAM, and this is a scalability problem. As we discussed also, a variable rate refresh can also be done because some rows can retain data much longer than some other rows. As a result, you can actually use this information to do the maintenance operation more efficiently. So this can be done in self-managing DRAM. RowHammer protection can be implemented in self-managing DRAM also. So DRAM internally has RowHammer protection. And whenever an activate comes, if it's doing RowHammer refreshes, for example, internal target row refreshes, it can tell the memory controller, wait for some time. I'm fixing some issues related to RowHammer. It doesn't even need to say I'm fixing issues related to RowHammer. Memory controller, just wait for some time, basically. And memory scrubbing is another approach that has been employed. The idea is to, this actually especially employed in server systems today. What server systems today do is they periodically scan the entire DRAM and they look for errors and correct them. This requires some error correction code mechanism, usually employed in server systems. But this periodic memory scrubbing actually has a lot of performance overhead if you do it very frequently. And this actually can be done also inside the DRAM chip more efficiently. But this requires the DRAM chip to have some time. Whenever it's scrubbing some part of memory, for example, the DRAM chip can say, memory controller, if you're going to activate this row, unfortunately, I'm not going to activate this row. Wait for some time. So that's the idea over here. I'm not going to go into the details, but this eases a lot of things in DRAM. First of all, it partitions the labor between the memory controller and DRAM nicely, in the sense that things that can be done much more efficiently by the DRAM manufacturers can be implemented by the DRAM manufacturers by using this interface and doing these, let's say, refresh or RowHammer protection or memory scrubbing operations, and implementing them by themselves. So the memory controller is not responsible for them anymore. And DRAM manufacturers know a lot about the refresh, RowHammer protection, memory scrubbing, so they can actually implement this themselves. So it's a good division of labor. Today, we don't have the option, basically. DRAM manufacturers, as we discussed, they can implement target row refresh, but they have very limited breathing room. They have to put in these target row refreshes within the slack time that's available for refresh commands, for example. Right? So as a result, the changes that are proposed are often difficult to adopt in real life. So if you go to this sort of interface, which is a little bit more flexible, you can implement changes much more easily because you can do the changes in the DRAM chip without modifying the interface or the memory controller. So that's the idea, basically. And the paper has more detail, which I'm not going to go into. But after, well, there's some problem over here I need to solve, which is really a problem with these slides. Okay, maybe not. Okay, slideshow. Yeah, these use timings never do that. Okay, good. I think we had that problem before also. Yeah. So basically, once you have this sort of interface, you can implement new changes inside the DRAM chip without changes to the DRAM interface and the memory controller. And the paper has some results that show that if you implement all of these mechanisms together, with support from the interface, you can improve both performance as well as energy efficiency compared to conventional DRAM that does not implement these mechanisms. Okay, and if you're interested, Hassan recently delivered a long seminar on this topic that covers the SMD work as well as all of the other works he covered in his PhD thesis. I'd recommend looking at it if you're interested, because I think this sort of delay, this is a very different direction, right? If you think about it. Let me hide the floating meeting controls. It's trying to solve the problem in a different way by enabling more autonomy to the DRAM. It's not just this problem. It's actually some of the other scaling problems to DRAM that can be solved using this. Any questions? Yes, please go ahead.
Does it mean the DRAM itself has the Bloom filter, as you mentioned, and keep track of the activations?
Yes, exactly. So if you actually do this, yeah, I don't have it this slide over here, but if you actually adopt SMD, the DRAM itself would have the Bloom filter. So in fact, that's one of the proposals in the paper. If you read the paper, you will see the effect of that.
So it doesn't mean it's a process in memory, right? It's just a self-correction mechanism.
Exactly. Exactly. Yes. Yeah. It's not this is not processing in memory, but it's synergistic with processing in memory, right? If you're adding mechanisms to do computation in memory. These mechanisms are also relatively, let's say, easy to add because you're already doing computation memory. Okay. Okay. So there's more coming up in 2023 in RowHammer. There are very interesting works in security conference, as you can see. There are some solution works that are coming up in architecture conference also, which we're not going to cover. But there's essentially more to come. Okay, let me cover some more, and then we're going to take a break. Unless you want to take a break right now. Is everything okay over there? Yeah.
Yeah, it looks good. They opened the window. And
okay.
Everything's fine now.
Okay, that's a long latency window opening action, let's say. We're going to talk about latency, but yeah. So let me talk about future a little bit. Essentially, DRAM is clearly becoming less reliable, and due to difficulties in DRAM technology scaling, other problems may also appear, or they may be going unnoticed. In fact, if you discover some of these problems, it can actually be very important, like RowHammer has been. Clearly, read disturb errors have been happening in DRAM. Retention errors may be slipping into the field because retention testing is very difficult, as we will see in the next part of this lecture. And who knows what else may be happening, right? So it's good to actually fundamentally think about what else may be happening in our memory chips and what else may be causing errors and what else may be exploitable. Because these errors can also pose security vulnerabilities. And unfortunately, this is true for all memory technologies that we know of today. DRAM, flash memory, emerging technologies, they all have some problems, reliability problems that can manifest themselves as safety and security problems as well. We discussed flash memory briefly. We're going to hopefully discuss that more. We'll discuss emerging memory technologies in a future lecture. But as these memories scale, they all have some noise to tolerate. Some of the error mechanisms may be different. For example, a phase change memory has write disturbance mechanisms. But essentially, scalable memory technologies have problems. This picture is from a paper that we wrote that I mentioned last time. But you can see that there are many different error types that exist that are very well known in flash memory. Program interference, cell-to-cell interference, data retention issues, read disturb issues, as you can see over here. And there are many solutions that are employed today to solve these issues also. So this is a nice overview of the list of different types of errors and solution mechanisms. And this is from this paper. If you're interested, you can take a look at it. This covers the state of the art, well, 5 years ago, let's say, but still a lot of these techniques are employed in modern solid state drives. When we have a lecture on flash memory, we may cover that, but not right now. So this is an example of an intelligent memory controller, actually, that provides reliability, scaling, safety, and security. And flash memory is a great example of that, as we discussed last time. I believe all memories will need this. And DRAM is an example also of that. So the question is, how do we actually architect these future memories? This is a high-level slide. I will not spend a lot of time on it, but we need to build a lot of understanding. This is a difficult part. Last time, someone asked the question, can you model this in DRAM, right? So using tools, it's very difficult to do it, basically. But we should shoot for it, meaning find out how we can model them and discover these vulnerabilities, discover these reliability issues. This requires a lot of real device data and analysis, and I've been showing you that analysis a little bit. But this also requires developing reliable metrics to decide whether a chip is vulnerable or not. And then architecture is very important. How do you actually partition the duties across the stack so that you have a good solution? Self-managing DRAM is one example. RowHammer is another example of partitioning the duties, right? It basically says DRAM doesn't do anything. Memory controller does everything, right? That basically tries to live with the business model of today, right? So it's good to think about these different partitioning of duties. But you cannot give up performance and efficiency and area overheads. And I think patchability in the field is very important, basically. So if you can patch the solution in the field, program it, you can achieve much more. And design and test is really important also. How do you do online testing to detect RowHammer attacks or other reliability issues? I think it's going to be even more important in the future, because offline testing, after you manufacture DRAM manufacturers do a lot of offline testing. In fact, most of the cost of manufacturing today is testing, not just DRAM, or also in processors. But DRAM, actually, I think the cost is more than 80% of the cost is testing the DRAM chips. These testers are actually very expensive, and you need to spend a lot of time testing the DRAM chips to assure that they work. Even then, as you can see, errors slip into the field. So this reducing that such that we release, let's say, some chips into the field, and then we correct the errors online by testing the chips online, making them better online, is another approach to this. And I think this is a very good approach to think about. How do you design the system for online adaptation, online testing, so that you can design the system becomes better over time in terms of both security, safety, reliability, but as well as performance. So we'll see that when we talk about memory latency as well, but you can make your memory latency better using online testing methods as well. Okay, so I think all of this require rethinking the relationship between DRAM and the system. So we need better communication between the DRAM and the controller, and better coordination of DRAM and the controller, I think, going into the future. So these two works cover those aspects. And understanding is important. That's why we've talked a lot about these experiments that are done with real FPGA infrastructures. That's true for any memory, actually, not just DRAM, flash memory also. Emerging memory technologies, it's harder to build these infrastructures, but it's also important to do that. And we've discussed intelligent controllers. Now, let me go back to what we've started with. We've started with this bridge, right? And some of you are familiar with this bridge. And a bit flip happens to this bridge. And human beings have been building these bridges for thousands of years. Unfortunately, these bridge incidents have been happening. Basically, bit flips have been happening, as you can see. This is Minneapolis. This is Genoa. And this is more recent. Does anybody know where this is? I know this place very well. Let me show you more. Maybe you can guess where this is. Yeah, you should guess where this is. Maybe you already know.
Somewhere in Pittsburgh?
That's right, yes. You've never been on this bridge?
No, not really.
Okay, you have not gone around Pittsburgh that much then. So this is the Forbes Avenue Bridge in Pittsburgh. This happened in 2022, early 2022. And you can see that it was not good. There were no fatalities, but you don't want to be subject to that bit flip over there. So my point is, human beings have been designing bridges for 2,000 years, and you would think we get it right. Well, apparently not. But this is a fundamental problem, basically, of reliability. It's a law of large numbers also, right? You have all these bridges in the world. Maybe one of them will go, something will go wrong, and eventually you'll get a bit flip, right? And I don't believe we're going to get it right, frankly, because getting it right comes at extremely high costs. With a lot of inefficiency, potentially, you can get it completely right. And it's a lot more difficult in bridges also. I don't think we're going to get it right in computing also, meaning I believe we're going to get these bit flips in some way or the other. But we need to prevent them, basically. We need to make sure that they're contained and they don't cause problems. In computing, we're a lot more lucky, let's say, because if you look at bridges, it's very hard and heavy infrastructure. How do you fix these bit flips? Well, you have a lot of trouble, right? Whereas in computing, we can be much softer. If you actually have a patchable memory controller, programmable memory controller, or programmable DRAM, you can avoid such failures much more easily. So we should really think about that going into the future. That's why we've been basically proposing these intelligent controllers going into the future. And I think they're going to be even more important. So this work, for example, was published in 2013. Today, we're in 2022, and we already have some intelligent memory controllers in DRAM. I think in 2032 or 33, we're going to have even more. So let's see. So the good news, industry is also aware of it. This is a paper that was written by Samsung and Intel. This is going to be one of the papers that I recommend in your homework also. But these folks discuss DRAM process scaling challenges. And they basically say there are a lot of challenges we have. They don't talk about RowHammer here, even though we were working with Intel about RowHammer in 2012, starting 2012. This paper was published in 2014. They basically say we have a lot of challenges, and it's going to be very difficult to solve these challenges at the circuit and device level. So we need to have intelligent controllers to solve this. And one of the solutions that is proposed in this work is in DRAM error correcting codes. And that's already happening, basically. There's error correcting codes inside the DRAM chips. I'm going to mention that in the next part of this lecture, hopefully, when we get to it. And there are some other solutions over here, like sub-array level parallelism. But intelligence in the memory control is actually going to be important. Now, let me give you some final thoughts on RowHammer, and then we're going to take a break, and then let's see how it goes. Any questions? People are very quiet today. Any solution ideas? Any new ideas that anyone has come up with? I'm very interested in those ideas. So you can actually make a big difference if you have some ideas. Okay, maybe in the future. So as I mentioned when I was discussing RowHammer, RowHammer is actually an example of Byzantine failure. So what does this mean? This slide is copied and pasted from one of my former colleagues at Carnegie Mellon, Satya. He's a pioneer in distributed systems. And he basically teaches the Byzantine failures, which I'm going to mention in the class, in the next slide especially. And he says he uses RowHammer as a real-world example of a Byzantine failure. So what is a Byzantine failure? Essentially, a Byzantine failure is characterized by undetected erroneous computation. You have some computation, you get a bit flip, and it's wrong, but you don't know it's wrong. This is opposite of a fundamental principle for dependability. When you have an error, fail fast. Basically, quickly figure that out and fail if you're going to fail, unless you can correct it, of course, right? Unless you can correct the error. Either give an error or give no result, but don't do undetected erroneous computation, because undetected erroneous computation can give you completely wrong results. And erroneous can be malicious also. The distinction is only the intent of the person who's taking advantage of the or who's manipulating the erroneous computation. Basically, a bit flip can be used to take over the system. That's malicious, or change your, I don't know, make your neural network completely inaccurate, right? And it's very difficult to detect and confine these Byzantine failures. Basically, do all you can do to avoid them. RowHammer is something that you should do all to avoid. And Byzantine failures were introduced by Lamport in the Byzantine generals problem. How many people covered this work in any of their courses? Okay, well, one person. So you've taken some distributed systems course, I assume.
Yeah.
Okay, good. Yeah, because distributed systems courses should cover this. And because it's posed as a distributed systems problem, I will just mention the problem to you, but there's a lot of work on this, especially recently with the advancement of blockchain, for example, and distributed ledger. This is becoming even more important. Assuming those things take off, you need to solve these Byzantine generals problem, because somebody can be manipulating your computation so that you get the wrong result or something even worse, right? So I will read the abstract of this paper. This paper had a lot of influence in the field, and it led to a lot of development of Byzantine fault tolerance techniques. But let's read it quickly. It says, reliable computer systems must handle malfunctioning components that give conflicting information to different parts of the system. This situation can be expressed abstractly in terms of a group of generals of the Byzantine army camped with their troops around an enemy city. Communicating only by messenger, the generals must agree upon a common battle plan. So you can imagine some generals, and they're far away from each other, but they're trying to attack the city. And they can only talk with each other using messengers, oral messages, which are described in this paper more clearly, of course, more robustly. However, one or more of them may be traitors who will try to confuse the others. Basically, they're erroneous compute engines, right? So in fact, not only the general, but the messenger can be a traitor, right? So this paper covers any fault in this distributed system of generals and the messengers, where generals need to agree upon an attack plan. Either they say attack or retreat, for example. Even the simple problem is not easy to solve if a fraction of the generals or the messengers are traitors, meaning they deliver wrong messages. They don't need to be traitors. They may actually be delivering a wrong message somehow, right? A bit flip, essentially. And the abstract continues by saying the problem is to find an algorithm to ensure that the loyal generals will reach an agreement. It is shown that using only oral messages, this problem is solvable if and only if more than 2/3 of the generals are loyal. So a single traitor can confound two loyal generals. And you need to read the paper to really understand this proof, but this is a very strong, proof that basically says 2/3 of the generals must be loyal for this to work. Basically, 2/3 of the machines should be acting correctly for you to reach an agreement. Now, this is stronger than majority voting, if you think about it, right? Because now we're a distributed system. There is no centralized decision maker. if you have a centralized decision maker, majority voting can work. But here in a distributed system, 50% or 51%, 50% plus doesn't work, as you can see. You need to get 66+%, which is 2/3, more than 2/3, because it's a distributed system. And then they say with unforgeable written messages, the problem is solvable for any number of generals and possible traders. Applications of the solutions to reliable computer systems are then discussed. So this is the extent to which I will cover this work, but I will say that this paper proposes some solutions that are not very practical. Later works built a lot of solutions that became practical over time. And blockchains, for example, use some practical solutions for Byzantine fault tolerance. The issue is there's still a lot of overhead. So the practical solutions still have a lot of overhead. So one of the issues with these distributed ledgers or blockchains is really the overheads to make sure that the system works accurately. Basically, everybody agrees on an account balance, for example, right? Or everybody agrees that a transaction has been performed, even though it's a distributed transaction, given that there may be someone who's erroneous or malicious, even worse. Okay, any questions about this? Okay, and the errors can be caused by RowHammer, basically, but it could be caused by any reliability problem also, actually. Okay, let me also mention some work that's relatively old as well, not as old as the Byzantine generals problem. But before RowHammer, people actually were concerned about bit flips. People actually showed that using, by introducing bit flips in a machine, you can take over the Java virtual machine. So this work actually has shown that. And you can read the abstract, etc. I'm not going to do that. But the way they induced bit flips was not easy. They basically had physical access to the machine. And let's take a look. This is an example of, well, this is the way they induced the bit flips. There's a lamp over here that heats up the memory so that you get a lot of bit flips in memory. So they had to have physical access to the machine so that, and they showed in this beautiful work that if you have these memory errors, you could take over the Java virtual machine. You could gain essentially virtual machine level privileges as a user level program running on the virtual machine, which should not happen also. It's not as bad as taking over the kernel. These folks did not go all the way to show the kernel, but this is also early work, as you can see, about 20 years ago. So this is interesting, and clearly this work has had impacts. I actually read this work long before we did the RowHammer work, and I thought it was very clever and beautiful. But what where RowHammer made a big difference is it essentially replaced that lamp with software. Now you can induce a simple memory error with software, using even remote software, right? You don't even need to be running your software on that machine. You could do it remotely through JavaScript. That's why RowHammer became very, very interesting for security folks. That's why there's a lot of impact in the security community. There's a lot of works that are going on in the security community saying that, oh, we have these bit flips and we can induce them through software. So this is actually a huge problem right now. Before, not many people cared about this lamp. Why? Because if you want to induce an error in a machine using this lamp or something like this, you need to have physical access to that machine, right? And that physical access is very difficult to get. But as user level software, you can have access to almost any machine in the world, unless it's strongly protected. Okay, so that's why RowHammer enabled a new mindset that enabled a renewed interest in hardware security research in general, because it shows that real memory chips are vulnerable in a very simple and widespread manner, and this causes real security problems. And also in the reliability domain, like dependable systems community, people were always worried about the connection between hardware reliability and security. This showed a direct way in which a hardware reliability mechanism can be exploited as a security vulnerability. And it's part of mainstream discourse right now. As a result, this is the reason, this is a historical perspective for you. This is the reason why we see lots of RowHammer attacks today, and many new RowHammer solutions also. Well, hopefully we will have more solutions, let's say. But if you're so inclined, you can develop attacks and solutions. Actually, past people who have taken this course were excited about developing attacks and solutions, and they're working on this sort of research right now. And there's more to come. I should say this more to come is really important. I believe there's a lot more to come in this direction with RowHammer, as well as RowHammer inspired type of problems. But most importantly, I think from a security perspective, especially a security researcher perspective, the fact that general purpose hardware is fallible, and the fact that it's demonstrated in a very widespread manner using RowHammer, create a lot of excitement, and also create a shift of mindset. People started thinking that, okay, there are hardware issues like this, like RowHammer. What else is down there? So they start examining hardware in more depth, and they start understanding the inner workings of the hardware and its vulnerabilities. And I believe it's no coincidence that two of the groups that went on to discover Meltdown and Spectre heavily worked on RowHammer attacks before. Now, once your mindset shifts saying that, oh, hardware is vulnerable, it's not just about software, we should really look at hardware. Now people started really finding these vulnerabilities. So Meltdown and Spectre. How many people know about Meltdown and Spectre? Okay, how many people do not know about Meltdown and Spectre? Okay, so that's a good fraction actually. So Meltdown, let me quickly give you the idea. We don't have time to cover clearly every security vulnerability here, but Meltdown and Spectre are security vulnerabilities that are demonstrated in essentially all high performance processor chips. These are CPUs, Intel, AMD, Apple, ARM, essentially everything, let's say, that employs out of order speculative execution and caches. And the idea is you have a side channel. Because of speculative execution, you can essentially infer data that you're not supposed to access. Because essentially, well, you're not supposed to access some data, but you can infer what's going on by looking at what is brought into the cache by some other program that accesses some private data, or some other part of your program that accesses some private data that this part of your program should not access. So that's the idea. It's a side channel that exists in all commercial processors that we know of. And this created a lot of, let's say, buzz in 2018, early 2018, when this was exposed, saying that all of the chips are not secure, etc. And it still goes on, basically. People have proposed solutions to it, but providing good solutions to this sort of side channel is not easy today. Academic work continues, of course. Also, industrial work continues. But essentially, it's analogous to RowHammer, because RowHammer is a bit flip, but this is a side channel. RowHammer bit flip can be used as a side channel also. That's the interesting thing about inferring information about something that you're not supposed to access. So in that sense, these are related, but they're completely different vulnerabilities in the end. Okay, but people are discovering these, and every, let's say, there are many security conferences as well as architecture conferences where people report new side channels in hardware that are inspired by these works. I believe there's more to come. It's always good to examine what else is lurking in hardware. What else are security vulnerabilities? How big are they? How important are they? And how can we exploit them? And how can we patch them? Why is this so important? I think people realize that hardware is really the root of trust in the end. Because you can do a lot of things in software, patch things, but in the end, if you cannot trust the hardware, everything that you in software can break down. And RowHammer is a great example of this, right? It shows that a bit flip in hardware enables you to circumvent all virtual memory protection mechanisms, right? And that's a huge problem. That's why we need to look more into hardware and ensure that we have a good, secure root of trust in hardware. So let me conclude. Any questions on this? Okay, one more. Please go ahead.
I was wondering what's the rate of bit flip, like can damage the data? Because I guess in memory, in many data processing techniques, you can tolerate some bit changes, right?
Yeah, so that's a great question. Yeah, so that's something that needs to be explored, I think. But there are a lot of works. Certainly, if your application is very tolerant to bit flips, and these bit flips are not used to for compromising your security, you may be able to tolerate some of the bit flips. But our work shows that your bit flip rate is very, very high. Basically, if someone is maliciously doing this, you get a huge number of bit flips, and those bit flips are not really, based on our own work, are not really tolerable by, for example, machine learning inference that is done today. But it depends on the application in the end.
Yeah, like, can I know generally what's the ratio?
Oh, I think, well, I don't have the number over here, but you should take a look at the Uncovering Target Row Refresh paper that has a bit flip rate. Yeah. Okay. Do you remember, Giray? Anything off the top of your head?
Not really.
Okay. Yeah, you should really look at the paper, but it's quite a high number.
like 10% or 5% or
Yeah.
20%, like what's high?
It could be even higher. It could be, I think,
Okay.
yeah, 30, 40%, 50%. Yeah. Okay. Yeah. Okay. Okay. So I see no other hands up. Let me summarize. Memory reliability is reducing. These reliability issues open up security vulnerabilities as well. They're very hard to defend against, and RowHammer is a prime example. As we discussed, it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And its implications on system security research are actually quite tremendous and exciting, and there's a lot going on. But that's true for architecture research as well. The bad news is I've kind of given you a lot of bad news. RowHammer is getting worse, and there's no indication that this will become better because we're scaling the technology, right? And it's a technology scaling problem. The good news is, I think as researchers, as people who can move the field, we have a lot more to do. I think we are fully aware that there's a problem, and there are other problems that may be lurking. And people are developing both attacks and solutions, understanding the space. And hopefully, we're developing even more principled models, methodologies, and solutions. And again, I will mention this work that for people who want to get into RowHammer quickly, well, we had a detailed lecture, but there are other detailed lectures that you may want to look at if you're interested. Okay, I'm going to skip these because these were part of the slides. But I should mention that there's a lot of work that went on in the group on RowHammer, and there's still a lot of people who are doing work in the group. If you're interested in directions, you should definitely talk with people like Giray, who's over there, Ataberk, Haosong. I don't know if I cannot see everyone, but they're doing a lot of work in this group, in the topic. I should also mention that clearly we covered this in computer architecture course, right, as a topic, but we, there's a digital design and computer architecture course. Kaveh Azavi's course, I don't have a slide over here, on hardware security, covers a lot of RowHammer as well, if you're interested. But we also have some project and seminar courses where we have coverage on SoftMC, which has enabled a lot of these discoveries and understanding. And also a Remulator, which has enabled the evaluation of solutions significantly. So there needs to be a lot of infrastructure to really understand these, and that infrastructure is really important to build. Okay, this is a great place to take a break, I think. Any questions before we take a break? Okay. So I think let's take a 10-minute break, and then we will continue. And then hopefully we'll end early, but let's see. I'll ask you a question, whether you want to learn about the history of RowHammer reviews. So you may want to think about that before we come back from the break. Okay, enjoy your break. Okay. Can you hear me?
We can.
Okay, good. Yeah, let's get started in a minute. Okay, if people are ready, let's get started. Let me see, folks are coming in. Okay. Okay, maybe I'll here ask the question. We can spend some time talking about what the reviewers said about the RowHammer work when they first saw it. This could give you insight into how the review process goes in academic circles. Is this something interesting? Who would like to spend some time on this? I guess raise your hand if yes, if the answer is yes. Okay, I see some hands. If the answer is no, who would like to spend some? I don't see a lot of hands. Maybe one? Don't be shy. It's okay to say no. Okay. Okay, even if you're saying no, you're outvoted because I don't see a lot of hands. Okay, so let's spend some time on this one because I think this is important. This also gives you an idea of what how people react when they see something that's let's say completely different or unusual or something they don't want to believe in, let's say. And usually the reaction is not completely positive. So, okay, basically, we've already talked about RowHammer. Clearly, it's the first example of how a circuit failure mechanism caused a widespread system security vulnerability. And now we have the advantage, after about 10 years, to see a large body of work that it has led to, right? In security attacks, mitigations, architectural solutions, analyses. In fact, architecture conferences are publishing many microarchitectural solutions to RowHammer these days. And work building on RowHammer still continues, clearly. But initially, it was dismissed by some reviewers pretty strongly. It was rejected the first time it was submitted to the Micro 2013 conference. So it could have appeared 1 year earlier, technically, but it didn't because it was rejected. I'll show you some of the reviewers and we'll discuss the reasons for rejection. But again, this is not the only work that gets rejected. So there are many works that get rejected because of, let's say, problems in their use system. I'm going to talk about that also. So these are the reviews that we've got. Let's say you can see that there's 6 reviewers. And you can see overall merit of 1 means that it's the worst possible grade a paper can get from the reviewer. Basically, a strong reject. You can take this paper over my dead body or something like that. Whereas 5 means that it's, I believe this may have been the highest score, but I'm not sure. So you can see that there 2 strong rejects, 2 weak rejects, and 2 positive reviewers. But in the end, it was rejected from the micro conference. Let's take a look at the substance of the reviews. So the first reviewer says security is not realistic, essentially, which is a very strong claim. This is one of the most negative reviewers. Like you can see the strengths, any results and observations, insights on how, well, there's some mistake over here, but they may happen. But it's interesting. Whereas they show disturbance may happen in DRAM array, authors don't show it can be an issue in realistic DRAM usage scenario. So what is it? What this means is, well, okay. I'm not fully convinced that the disturbance problem is going to be an issue in a realistic DRAM usage scenario, main memory with caches. In that scenario, 64 millisecond refresh interval may be enough. Overall, the work presented, the experimentation, and the results are not enough to justify a claim that disturbance may be an issue for future systems and that microarchitectural solutions are required. So you can see that's quite subjective, let's say. the reviewer doesn't buy the fact that there could be a potential attack that can be constructed on top of this. And they're not taking any issues with the results. It's just a subjective opinion, as you can see, which is going to be something that I recommend other people not to do, basically, in general. You may have your subjective opinion, but stick to the objective facts. You may believe that that's not a real issue in real programs, but the objective facts in the paper are something else, right? So that's one important thing when you review things scientifically. If you're doing subjective facts, then you're in the business of politics, and everybody's doing that, right? Then we're not scientists at any point. We're basically reduced ourselves to, I don't know, opinion columnists or newspaper writers or politicians, right? That's what they do, basically. They even throw a lot of lies, essentially. So essentially, the reviewer says, I really encourage the authors to address this issue, run a new set of experiments. If the results are positive, the work is great and will be easily accepted in a top-notch conference. The test scenario in the paper, open, read, close a row many times consecutively, that's used to create disturbance, is not likely to show up in a realistic usage scenario. So our answer to this, there's a rebuttal process. So the reviewer, we don't know the identity of the reviewer. That's why it's a reviewer A, right? That's a double-blind review process. They're supposed to not know the identity of us also, but I'm not sure about that. I definitely know that I don't know the reviewer. That part I'm sure of. But basically, the question is, will it affect real workloads on real systems? Another reviewer also raised this issue. So basically, our response is this: malicious workloads and pathological access patterns can bypass or trash the cache and access the same DRAM row a very large number of times. While these workloads may not be common, they're just as real, meaning security is real, right? There could be attacks or workloads that are constructed by someone for a malicious purpose that do this. Of course, unfortunately, our rebuttal didn't work. So there's a other part of the rebuttal that I just omitted here, but it goes into more technical stuff. Okay. So reviewer A also demands some things that are a little bit not realistic based on what we have discussed in the last lecture. To make sure that correct information and messages are given to the research community, it would be good if the conclusions drawn in the paper were verified with the actual DRAM manufacturers, although I can see that it can be difficult to do. In addition, knowing the technology node of each tested DRAM would make the paper stronger and would avoid speculative guesses. So we actually did verify this with 2 DRAM vendors who did not want to go public at the time. Okay, but that's reviewer A, as you can see. So based on these comments, the reviewer strongly rejects the paper. This is the worst possible score a paper can get. Any thoughts? Okay, interesting. Yeah. Well, I mean, once you start doing work that no one has done, you can easily get this sort of comments, as you can see, right? But I'd encourage people to be objective, not subjective. Let's take a look at reviewer C. There's also another reviewer who rejected the paper. It's weaker, as you can see. You can see the weaknesses. You can see the strengths over here. Measurement methodology is outstanding, and the authors very thoroughly dive into different test scenarios to isolate the circumstances under which the observed errors take place. And then the weakness. This is an excellent test methodology paper, but there is no microarchitectural or architectural content. Unfortunately, this is wrong because clearly there are solutions that are proposed that are microarchitectural or architectural. And then the reviewer says, my primary concern with this paper is that it doesn't have microarchitectural content and may not spur on future work, which probably the reviewer was wrong on. Yeah, I mean, I'm not going to read the entire review. It's very subjective, right? It's not really taking into account the objective. Okay, what's proposed in the paper? Is it solid? Clearly, the reviewer agrees that it's very solid and rigorous, and the results are good. But the reviewer's issue is this doesn't belong here on a wrong premise, because there is actually arguments in the paper made saying that this does belong here. Here's a solution: probabilistic adjacent row activation. That's a microarchitectural solution. In the end, it was employed actually by future vendors as well. So you can also read this. This is also interesting because you can see there's a positive part. That being said, disturb errors have occurred repeatedly over the course of DRAM's history, which the authors acknowledge. Yes, but none of them were exposed in real DRAM chips. So disturbance have been documented in DRAM clearly. Yes, people have tried to simulate it. People have tried to test it. Unfortunately, there's no work that shows that it happens in real DRAM chips. And that's the key contribution of this work. So the reviewer is a bit, let's say, over claiming over here. History has shown that particular disturbances and in particular hammer errors are short-lived and are quickly solved by DRAM manufacturers. Historically, once these types of errors occur at a particular lithography node DRAM density, they must be solved by the DRAM manufacturers because even if a solution for a systemic problem could be asserted for particular markets, blah, blah, there will always be significant DRAM chip volume in single-piece applications like consumer devices where complex architectural solutions aren't an option. You can see that this is completely opinion, commentary. There's nothing here that takes issue with any result in the paper or any methodology in the paper, basically. So this is very bad, basically. I would say that if you ever review a paper, never do something like this. Even if your opinion may be interesting. Yes, it's an interesting opinion. I completely disagree with this opinion also, because this is not true. Clearly, as history has shown, complex architectural solutions are an option. Today, people are implementing those solutions, right? We saw using trespass. We know what uncovering TRR. There are architectural solutions inside the DRAM chips. So history has proven this opinion wrong completely. But this reviewer takes this opinion to reject a scientific paper. So very bad, as you can see. So the authors have identified a contemporary disturb sensitivity in DRAMs, but as non-technologists, our community can generally only observe, not correct such problems. Okay, another opinion, basically. And it's in fact, I believe this is a very backward-looking opinion, saying that, oh, this is a problem I cannot solve. Let somebody else solve it. This is, again, very bad mindset also. It's not just an opinion, it's also a reflecting mindset. And you can see that the reviewer rated themselves as expert in the area with highest confidence in their review. So this is the highest possible rating you can give to yourself as a reviewer. I would say maybe reviewers should be stepping back a little bit and thinking about what they opinionate on as opposed to objectively evaluating the paper. Okay, reviewer D, let's take a look at this also. This is also interesting. Basically, the gist of this review is nothing new in RowHammer. You can see another expert and a very strong reject. Okay, let's look at the strengths over here. DRAM errors are getting okay. I mean, it's not a very strong evaluation of strengths. The weaknesses, the mechanism investigated by the authors is one of many well-known disturb mechanisms. The paper does not discuss the root causes to sufficient depth and the importance of this mechanism compared to others. Overall, the length of the sections restating no information is much too long in relation to new work. This is also very interesting. I would say that this is a hatchet job, let's say. It's trying to basically kill the paper. That's it. They just don't want to see this paper. I wonder if this review is coming from some, let's say, DRAM manufacturer or someone basically who has some interest in rejecting the paper. Of course, we don't know, but because this is not true. I mean, none of the analysis, as anybody who is working on RowHammer would attest to you, none of this analysis that's done in this paper was done in any other paper. It's or anything else, basically. It's just it's analysis on real DRAM chips also. Okay, you can see that insignificant novelty. Okay, so the paper was rejected, as you can see, and there's no there are other parts of the reviews, but these are short reviews actually, and there's no substantial comment that takes issue with the results in the paper, as you can see. It's more opinions. Now the good news is it was submitted to the next conference. You can see the submission date over here, 21 November, and it was accepted in the next conference. And you can see the reviews look like this. It's a different scale over here, but you can see that there are still 2 reviewers that are opposed. Some reviewers are actually quite strong. I think 8 was the largest number over here. It says award quality paper. We should definitely accept it. But some reviewers are basically strong reject. There's a 1 also, but nobody gave a 1 in this case. That's good. That's why probably it was accepted. Let's take a look at these reviewers who reject the paper. Basically, one of them says, already done on YouTube. This is actually a very funny comment. You can see this over here. What you demonstrate in this paper is so-called DRAM row hammering issue. You can even find a YouTube video showing this. This YouTube video is like, it covers RowHammer. It's from a manufacturer called Teledyne LaCroix. And I know them very well because I interacted with them before their YouTube video was published. But basically, they show a memory controller, memory tester. These folks sell memory testers, and they basically test memory. And they basically, in a very brief part of the video, they say we can detect row hammering patterns using our tester. That's it. That's the row hammering part of the video. You can check for yourself if you're interested. And this reviewer uses this video to try to reject the paper, as you can see. It's very unfair, in my opinion, and you should never do that also, because clearly a 2-minute part or maybe a 30-second part on a YouTube video is not covering a full scientific paper. These folks do not even analyze the problem on real DRAM chips. They don't provide any data, basically. Okay, so you can see that this is also an expert. I mean, you can read this over here, but in the end, he agrees that the reviewer agrees that this is a well-written and executed paper, but it's already done, basically. Interesting. Okay, reviewer D. I mean, you can see the review over here. They also have other issues, which is the relevance of this paper to ISCA. I feel that this paper is more appropriate for conferences like International Test Conference or VLSI Test Symposium or Dependable Systems and Networks. This is because the authors mainly dedicated the effort to the DRAM circuit characterization and test method, in my view, while the architectural contribution is very weak. You can see the wording that's used that's trying to denigrate the paper, right? This is actually a very unfortunate fact that I believe these reviewers are not... they don't have anything at stake to lose, basically. The reviewer can say anything about the paper and that's it, basically. There's no accountability to the reviewer. I'm not even sure this can be published to these venues since it's a well-known problem. Oh, yeah. I also assume techniques proposed to mitigate disturbance error in STT-MRAM and other technology can be employed here as well. So you can see that the reviewers are, again, using reasons that are not objective to reject the paper. Oh, this is appropriate for some of the conference, but I'm not even sure it should be published there. This is quite relevant to ISCA. I believe history has proven that it's quite relevant to these conferences because there are right now a lot of other papers that are published on this topic on these conferences. So history is always a good corrector, let's say, especially of wrong things. In this particular case, we have the good hindsight. But you need to, unfortunately, you need to be resilient to this sort of comments and push your ideas forward so that they're published, so that they can have their impact. Okay, this is a rebuttal to reviewer D. I don't want to spend a lot of time over here, but I think reviewer D also says, oh, there's some patents. We already cite those patents. These patents don't provide real data. In fact, these patents that are trying to solve the problem actually, well, these are some other patents. These are some citations on wordline coupling, for example. And clearly, disturb issues were shown in simulation, but never shown in real DRAM chips. So this is actually interesting. Anyway, you can read this on your own if you're interested. This rebuttal argues basically that that past works are different. But again, I don't know if the reviewer bought it, but the paper got accepted in the end. Probably other reviewers were a lot more positive about it. Let's take a look at one more over here. Again, similar thing. Row hammering appears to be well known, and solutions have already been proposed by industry to address the issue. Now that you know the hindsight, you know that solutions don't even work, right? Some of them, and these are not even the solutions that were proposed by industry at the time. There were some solutions that were proposed. For example, this patent. For example, Intel has a patent and application on a memory controller technique that addresses the exact problem with priority date. This is the time when we were working on RowHammer together with Intel. At that time, they published some patents. And yes, it's basically detecting aggressor rows and refreshing them. So it's an access counter-based mechanism. And yeah, you can read the review for more detail over here. And we have a rebuttal, as you can see over here. We actually cite these patents in the paper right now and include a comparison. Okay, so these are the patents. If you're interested, actually, these were patents that were made public in 2014. And clearly, these patents have no data. They just basically provide information about how you can fix the problem, which they don't provide a lot of information on. Okay, so I just gave you a sampling of the reviews. And I mean, you can have your own opinions about the reviews, but I find these very unfair and subjective. They don't really talk to the substance of the paper. In fact, in many cases, they provide wrong comments, right? Oh, a YouTube video demonstrated this. What did they actually demonstrate? It's good to think about that. They just said we can test for hammering patterns in DRAM. Does it really make sense to dismiss an entire paper that provides a lot of valuable data, including data showing that you can induce these bit flips in real DRAM chips just based on that? So I think any reasonable person would say this is completely unfair. But unfortunately, this is the review process that happens today. We should be better than politics, but unfortunately, in some cases, we're not better than politics. So that's why I mentioned these suggestions to reviewers. People need to be open-minded. They need to be accepting of diverse research methods. There's no single way of doing research. This targets basically, oh, this is not an ISCA paper. This is not an architecture. This is testing. Well, everything is related. And here, it's really a lot about architecture, actually. And people need to be constructive, objective, and not have double standards. Basically, unfortunately, I think because of reviews and reviewers like this, scientific progress is being delayed. So I could imagine our RowHammer paper being published 1 year or 7 months before. And it could have enabled a lot more progress in the field, a lot more solutions by now. 7 months is not bad, actually. Some papers get delayed by 2.5, 3 years before publication, just because reviewers have these subjective comments. It's good to actually think about like publications also. So this article from the Wall Street Journal asked the question, could Einstein actually get published today because of all of the bureaucracy in publication? And they argue that probably not. And of course, we know that Einstein has done some seminal work, right? And he had a particular style of writing his papers. In fact, a lot of his papers are not backed up by data. It's just theory. And he doesn't even prove the theory. He says basically data will hopefully come in the future, right? So that's how, unfortunately, research community has been restricting the scientific progress a little bit, in my opinion, today. We need to be a lot more open to big things. And we should be a lot more objective as opposed to subjective. Okay, I think Juan covered some of this, but I would recommend this book again. This book is The Art of Computer Systems Performance Analysis. And this book, aside from being the seminal scheduling theory book of its time, it has a lot of interesting points. For example, the author, Rod Jane, says, even if the performance analysis is done correctly and presented correctly, it may not be enough to persuade your audience, the decision makers, to follow your recommendations. The list shown in next box is a compilation of reasons for rejection heard at various performance analysis presentations. And it says you can use the list by presenting it immediately and pointing out that the reason for rejection is not new and the analysis deserves more consideration. Also, the list is helpful in getting the competing proposal rejected. So that's actually tongue-in-cheek, of course. So basically, people can take issue with lots of things. We'll cover this later on also, but you can see at the end, you can reject things by saying this needs more analysis. That's one of the top things. Or that's beyond today's technology. This impacts hardware. And then the last one is why change? It's working okay, right? I think one of the reviewers had this mindset. Oh, this doesn't affect real applications. It's working okay. Let me move on. Let me reject this paper completely. That's essentially the same mindset that this book alludes to or describes. So in a sense, that's nothing new. There's nothing new in these reviews also, unfortunately. But I think the review system caused this. So this review was received after the paper was published, like about 1 year after the paper was submitted to IEEE Micro Top Picks, which is supposed to select the top papers of the year. Usually they don't select the top papers of the year. But basically, you can see how people react. One of the reviewers react. I'm not going to spend time on other reviewers, but this reviewer subjectively, very subjectively says, I poked around a bit and DRAM vendors have already solved this problem. DRAM row hammering appears to be an old problem. And you can see that I seem to remember that during the presentation at ISCA, it was pointed out that the DRAM manufacturers have already fixed the problem. So where is the novelty and long-term impact? That's what they're looking for, as you can see. So, but in hindsight, we know that the problem is not fixed today. I mean, we discussed works from 2020 and 2021, right? This review was written in 2014, I believe. Okay, so that's why I have these suggestions to reviewers. So I believe we need to somehow fix the reviewer accountability problem. If you're doing scientific research, the reviewers need to be accountable based on what they say. I think accountability is really important everywhere, right? We have a huge problem with accountability in politics, I think, everywhere in the world, not just here or the United States, but everywhere in the world. But we also have this accountability problem in scientific research where it has no business to be in my opinion. So reviewers are not accountable, so they can make these subjective comments and they can get away with it. That's the problem. So just like main memory needs intelligent controllers, as Juan convinced you, research community also needs accountable reviewers so that it can work. So that's why I think I suggest to people a bunch of suggestions you can read. But I think in the presence of this, what should the authors do, right? You can see there's a hostile environment, not so good, let's say, for publishing your research. I'm not saying the entire environment is hostile. There are some reviewers who are very fair-minded, very careful. But unfortunately, they're not in the majority, in my opinion. So what should the reviewers do? I think, what should the authors do? I think authors or scientific researchers who want to do something really important, they have to follow their passion, basically. There will be these naysayers that appear. And you cannot really, unfortunately, you cannot basically give up if they exist. And they exist. That's the situation, unfortunately. Unless we change the review system, somehow they exist. As a result, people need to be resilient when they're conducting research. They need to focus on learning and scholarship. They need to be able to figure out sort the chaff from the weed, if you will, from the American term, right? You basically are doing a harvest, and there's a good part of the wheat, and there's a bad part of the wheat, and you need to get rid of the chaff so that you can eat the wheat, right? So there are some comments that you should be able to ignore or figure out that these are completely subjective things and they're unfair. So that's why you need to focus on learning and scholarship and push your ideas out. And in the end, the quality of your work defines your impact. I strongly believe this. I mean, this also in the end gets validated by history, in my opinion. But I think this requires hard work also, not just resilience, because you need to overcome. Clearly, research is hard work to begin with, but you also need to overcome these issues to get your research published as well. But I believe with a good mindset, goals, and focus, being resilient and working hard, you can make a good impact on the world. I've seen this many times. Later, I may give you the story of the Ambit paper, for example. It was rejected 4 times before it was accepted. I think Juan mentioned this a little bit, but I can give you a more personal story, but we don't have time for that today. Okay, so if you're interested, we cover some of these in some interviews and certainly in some videos as well. But this is one of the reasons I suggest Richard Hamming's paper for your research, because he covers some of these things, issues and research as well. And this dates back to 1986, as you can see. And that brings me to the end of the RowHammer lecture with some historical perspective on the review process as well. Any questions that you may want to ask about the review process or something similar? Not yet. Okay, there's one. Please go ahead.
I was wondering, have some suggestions of how those reviewers or the mechanism of reviewer could improve?
Mm-hmm. Yeah, you have some suggestions?
Because I think there always will be people reviewing. Like now we mostly rely on people, and people do a subjective reviews. Mm-hmm. So those are unavoidable, I think.
Yeah, I agree with you. Part of it is human nature, right? I think you're alluding to human nature, and humans are by nature subjective. They can have conflict of interests that are not necessarily declared, right?
I was wondering if there's some system verifying all ends of statistic, what is present, what is not present, what is novelty, instead of only people saying this is new and this is already on YouTube.
I see. I think that's very good. What you have in mind is nice. I don't know of any system, basically. You're trying to automate this somehow. Is there an automated way of doing these reviews or supplementing these reviews in some way or verifying these reviews based on past information?
You can't avoid it, especially like when they're reviewing huge amount of paper and their mind could just looking for an escape. It's not the intentionally made it. So
yeah, you're absolutely right. I think you're basically pressing on the right problems. There's overload. Even if the reviewer may not be malicious, It may be because they're basically overwhelmed, right?
Yes.
I think exactly. I think automating is very difficult because it requires a lot more advances in artificial intelligence, in my opinion. We still need to rely on experts, right, who know what's going on. But I think some things that reduce the potential, some things that improve accountability can help. For example, if the reviewer knows that their identity might be public, I think that actually helps a lot.
Yes.
Not necessarily immediately public, but their identity may be public at some point in time. Then that basically perhaps they may think that, okay, maybe I should be more careful about what I write, right?
Yeah, I think this credibility and issue actually relate to all aspects of human life, right? If you know all your behavior are recorded or can be recorded, you will be more careful.
Yeah, exactly. I mean, I'm not suggesting that it should be done in all aspects of life because there's some privacy concerns over here, but certainly in the review system where you're affecting an outcome that's affecting other people, you should base it on something that you should be proud of backing, right? If you cannot be proud of backing what you write exactly, you should not be writing it. So I think certainly this accountability aspect can be improved by making reviews public and the reviewer identity is public.
Yeah, definitely.
How much will it improve? We'll see, I guess. But that's a step in the right direction.
Yeah.
Okay, great. Any other comments, thoughts? Yes, please.
Have you ever had a situation with like a paper that just never got accepted?
That's a good question. Never. You should talk to some of my students, maybe. I think never got accepted is possible. Usually what happens is with our work, we put it on archive. When we believe a work is ready, we put it on archive. It's not published on archive, clearly. It's a preprint server, right? archive.org. But it gets, at least people look at it and the work starts having impact. And I encourage my students to do that sometimes even before submitting to a conference, because I believe that's good for scientific progress, right? Once you have some result that you believe is correct completely, put it on archive, and maybe the reviews should come on archive also, right? So has there been a case where the paper has not been published? In the end, I think there are some papers that we submitted after 9 times. They got published in a top conference. We had a recent case of that at Micro, for example. Sometimes the number was 11 times. You can imagine how long it takes. This takes we're talking about 3-4 years. So you need to be very persistent. And in the end, the paper gets into a top conference. And usually in many of these cases, not much changes in the paper. Usually the reviewers are very subjective. They're picking on something small in the paper. That doesn't change the major aspect of the paper at all. If that doesn't happen, sometimes you can send the paper to a less visible venue. Let's say there are some venues in scientific publication that are very prestigious, and sometimes this sort of issues happen a lot in prestigious venues. If you reduce the, let's say, level of the venue, visibility of the venue that you send your work to, some of these issues are not as bad. Let's say they could still be bad, but not as bad. So your work can get published, in my opinion, somewhere eventually. So you won't get starvation if you actually find a place to publish your work. Does that make sense? Okay, these are very good questions. Okay, I don't see any more questions. So let's switch to lecture 7B, sorry, and talk about data retention a little bit. I don't know if we'll be able to finish it, but I think it's important to talk about it. Let me close this PowerPoint window first. Okay, now you can see it, I think. That's good. Let me change this here. Okay. So we're going to switch gears a little bit and talk about another memory technology scaling problem with charge-based memories, DRAM specifically. But this is a problem with many memory types, like flash memory also has data retention issues. I'll mention that. Flash memory also had read disturb issues, as I I mentioned, but we didn't talk about exactly how it works. But these issues exist in all memory types, as we will see, to different levels. Okay, I'm going to skip this, but basically, I think the RowHammer work and the retention work and many works we'll cover help you understand how a computing system works underneath the software layer and how decisions made in hardware affect the software and program. We see all that's in RowHammer. But you should also be comfortable, hopefully by the end of this course, in making design and optimization decisions that cross the boundaries of different layers and system components. And I see RowHammer as an example of this, right? We showed solutions that fix the problem in the memory controller, inside the DRAM, cooperatively, etc. So there are actually a lot of interesting solution directions, and also at the software level potentially. So we'll talk about DRAM refresh. And as I mentioned, DRAM capacitor charge leaks, and you need to periodically refresh it. And we know if DRAM is in the system. I'm going to skip that one. We've already seen this also. A DRAM cell consists of capacitor and an access transistor. This is the capacitor. It stores data in terms of charge in the capacitor. And a DRAM chip consists of many, many rows of such cells, basically tens of thousands of rows. And every one of them leaks over time. And the memory controller needs to refresh each row periodically to restore the charge. And basically, this requires activating each row every n milliseconds. Typical n today is 64 milliseconds, but these are old slides. Today, typical n is actually 32 milliseconds because retention time has becoming worse in recent DRAM chips, even though DRAM manufacturers also employ in-DRAM error correcting codes inside the DRAM chip. So some of these errors due to retention leakage is corrected due to in-DRAM ECC. Even then, they had to reduce the refresh interval to 32 milliseconds. So you can see that this is actually a problem that is becoming worse. So there are many downsides of refresh. Clearly, each refresh consumes energy. You need to activate every row every 64 milliseconds. It causes performance degradation while you're activating a row, refreshing a row. DRAM rank or bank is unavailable depending on how you do the refresh. It causes some quality of service, predictability impact. Whenever a bank or rank is being refreshed, again, you may have a quality of service critical, latency critical request you may not be able to serve. And it turns out refresh rate limits DRAM capacity scaling, as we will see in a little bit. But first, some analysis. If you've taken digital design and computer architecture, I've already thrown this to you. We maybe have a homework question related to this also. But imagine you have a system with a large number of DRAM, large amount of DRAM, 8 exabytes. That's 2 to the 63 bytes. And today we can imagine such systems. Supercomputers actually are getting close to exabytes. They're definitely in the level of petabytes. But again, we're thinking about the future as architects, right? The exabytes are very easily imaginable today. Assume a row size of 8 kilobytes. That's 2 to the 13 bytes. How many rows are there? That's an easy question, right? That's you divide the DRAM size with the row size. That's 2 to the 50. That's a lot of rows. And that's going to increase. How many refreshes happen in 64 milliseconds? Well, today, if everything is refreshed every 32 milliseconds, the answer is 2 to the 50 times 2, right? Okay, that's a lot again, right? By the way, refresh has a temperature dependence, which we will briefly mention. And this is a very well-known property. And as temperature increases, you need to refresh more frequently because charge leakage accelerates at higher temperatures. So if you're operating your DRAM at higher temperatures, the refresh rate today can be as low as 8 milliseconds, like 16 milliseconds and 8 milliseconds. So at high temperatures, this actually becomes an even bigger problem. Okay. So what is the total power consumption of DRAM refresh? So you can calculate this based on looking up some data sheets. I'm not going to do that, but you'll get some, I think, homework credits if you answer the homework question. What is the total energy consumption of DRAM refresh during a day? You basically multiply the power with the number of seconds, time. Power times time is energy. So you will get that. And this is a good exercise to do, actually. And you will get, I think, some homework points if you do it. Right, Mohammed? We'll have a homework question related to this.
Yes, I will have.
Okay, something like this, I guess. Maybe not the exact numbers over here, but yeah. So you will get a very large number, basically. It's on the order of kilowatt hours, I think. But I'm not going to give you the answer because I don't know. But I'll give you a real world example that I found recently. I think this was yesterday or the previous day. I don't know if the audio is connected over here, but let's see. This is a leaky DRAM cell. We could keep watching this for about an hour or something. But okay, let's not do that. Yeah, basically imagine billions of these doing this. It's a huge waste rate. I mean, analogy ends at some point, but this clearly has many, many impacts in terms of energy, in terms of performance. If you need water, now where do you get it from? It's a huge waste, basically. So it affects performance in real systems, real DRAM chips. So this is based on our scaling study that we did in a paper that we published in ISCA 2012. On the x-axis, you see device capacity, DRAM chip capacity. On the y-axis, you see the percent of time the chip needs to spend refreshing. And you can see that as the chip becomes larger, 64 gigabits, the time spent refreshing increases significantly, 46% over here. Why? Because in a larger chip, you have smaller cells. That's the expectation. So the refresh rate should be higher. And also, smaller cells are leakier. That's why. Or they store less charge. So refresh rate needs to be higher. And in a larger chip, you have many more rows. So you have more rows to refresh. So you have more rows to refresh, and each row needs to be refreshed more frequently. As a result, performance overhead increases significantly. This is what we envisioned in 2012, basically, what will happen. It's kind of happening, but hopefully we're not going to be as bad because people are trying to solve the refresh problem. Energy is similar, basically. This is device capacity, a percentage of DRAM energy spent refreshing. This assumes how much your DRAM is active. For example, in my cell phone right now, nothing is really active. So most of the DRAM energy is spent refreshing. There are no applications that are running, as far as I know, that are accessing the DRAM. So almost all of the DRAM energy is spent refreshing right now. But in future chips, assuming some activation rate to DRAM, access rate to DRAM, again, about half of the DRAM energy could be spent refreshing. So again, this is not acceptable, right? If you want to have a viable DRAM chip, you should not spend most of your performance or half of your performance not being able to access the chip and half of your energy on refresh. But this number can go higher in idle periods, as I mentioned just now. So the question is, of course, how do we solve the problem? So I'm going to talk about some observations. So clearly, at the time we did the research, all DRAM rows were refreshed every 64 milliseconds. Critical thinking says, do we need to really do this? It's always good to question things, basically. Do we really need to do this? That's a basic question to ask, right? So what if we knew what happened underneath in DRAM cells and expose that information to upper layers? In fact, this question to ask, I think, critical thinking can be done anywhere, right? It's a life principle. You can see something out there. Do we really need to do this? Is a good question to ask. And you may have a fundamental solution that fixes some problems. So here the question is basically, more detailed question is, what if you knew what happened underneath in DRAM cells and expose that information to upper layers? So I mentioned this to you in the last lecture. If you look at the retention time profile of DRAM, it's very heterogeneous. There are some cells that can retain data for a small amount of time, like 64 milliseconds, a little over 64 milliseconds, but most cells are quite strong, actually. So most cells can retain data for more than 250 milliseconds. In fact, some cells can retain data of tens of seconds. If you're operating at low temperatures, they can retain data for minutes and sometimes maybe hours if you are good enough at testing, for example. So basically, there are some very weak cells and there are some very strong cells. So it's a distribution of cells in terms of retention time. The question is, can we take advantage of this? And the answer is hopefully yes, basically. And then you can brainstorm about many things. But let's first ask the question, why do we have such a profile? As we discussed last time, manufacturing is not perfect. You have some process variation. Not all DRAM cells are exactly the same. Just like not all fire hydrants are exactly the same, right? Some are more leaky, some are less leaky. And also not all people are exactly the same. Sometimes when they connect water to the fire hydrant, they will do it in different ways. So there's variation, as you can see. Variation is a basic principle of, let's say, a lot of things on the earth. And some cells are more leaky than others. And this is really manufacturing process variation in this particular case. So the question is, how do we take advantage of this profile? Assume that you know the retention time of each row exactly, because refresh is done on a row granularity, not cell granularity. You activate an entire row. What can you do with this information? Who do you expose this information to? How much information do you expose? And clearly, this affects a lot of things, as you can see on the slide. How do you determine this profile information? And who determines it? This is an across the stack problem again, right? You have some device whose retention time properties you may know. How do you determine those properties, and how do you expose that information to? So you could, for example, expose this information to the operating system, and the operating system says, I'm not going to allocate any rows that cannot retain data for more than 256 milliseconds. So, and then I'm going to increase the refresh rate of my system, or reduce the refresh rate of my system to every 256 milliseconds. Operating system can potentially do that. This causes some issues in the memory allocator. And this also requires you to have very good profile information, of course. But it's possible to solve this problem at that level, right? You can get rid of those rows that cannot retain data for long enough, for some definition of long enough. And hopefully you won't lose a lot of memory capacity. The trade-off here is that you lose some memory capacity because you cannot allocate some rows to the applications. And hopefully, if this retention time profile looks correct, or is correct in real life, most of the DRAM is still available for you to use. So that's a potential solution. That was actually proposed earlier. I'm going to give you some other solution. Any questions? Maybe you have some solution. Yes, please.
I just noticed that if you are going to differentiate for each row, then the memory allocation could be different per memory system or per system. Then it's not it's not scalable for all the manufacturers. You have to do this differentiation of cells every memory system.
Yeah, absolutely. Every chip, actually. So for every chip, you'll have to do it. Yes, you're absolutely right. So it's a solution that requires some testing, and that's one of the downsides of the solution. It requires a lot of testing, as we will see.
Yeah, it doesn't scalable, feels like.
Well, DRAM actually manufacturers do a lot of this testing, but you can actually do some of this testing online, as we suggest in our future works.
Okay.
So while the system is operating, once in a while you test the system and figure out this information incrementally over time. So as your system operates, you can actually become much better in terms of energy efficiency and performance if you do this online.
Yeah, that makes sense.
Okay, great. Yeah, that's why I mentioned online testing earlier when we talked about solutions to issues. Okay, so we did study this retention. Oh, there's a question in the back. Okay, please go ahead.
Couldn't you just have redundancy in the rows and then deactivate these rows that are slow in refreshing and just have like the ones that you don't need to refresh often? Yeah.
So that's a great question. Basically, essentially, you remap the rows, right? And actually, part of this is done today. If manufacturers discover some row to not have good enough retention time, they remap it to some other rows. So that's a good idea. That's part of it is already employed today. You can also do this dynamically, potentially, as you dynamically determine a row that doesn't have a good enough retention time. You remap it to a strong row. Okay. Some of these ideas were proposed in research. Actually, we may cover them in one of the papers. Copy row. We actually propose this idea that you mentioned, and we do it dynamically. This was in ISCA 2019. Okay, very good. What else? Any other questions or ideas? It's good that people are generating ideas. I like that. That's the purpose of this course. Enable you to generate ideas to solutions, problems that you may not have seen before. Okay, so we built this, as I mentioned in the last lecture, we actually built our DRAM infrastructure to test retention issues. So I'm going to give you some results based on that. So this is our first testing that we did. The first paper that we published based on our platform, and it's temperature controlled. We basically tested many DRAM chips from 5 major manufacturers, and we looked at 7 families, and we tried to do a scaling study basically based on our initial resources that we had. This is in 2011 we're talking about, and basically we discovered that this is true. This was not discovered by us. This was actually mentioned many times before. So retention time profile, but we figured out that in existing DRAM chips, some things are getting worse, as we will see. So basically, an overwhelming majority of DRAM rows can be refreshed much less often without losing data. You can see the numbers over here. So the number of cells in 32 gigabyte DRAM is very small, and these are randomly distributed across rows. So you can think of 30 cells and 30 rows, essentially. Essentially, 30 rows need to be refreshed every 128 milliseconds. And no, what should I say over here? 30 rows need to be refreshed more frequently than every 128 milliseconds, and 1,000 rows need to be refreshed more frequently than 256 milliseconds. So you can see the curve over here. The question is, can you exploit this to reduce refresh operations at low cost? There were multiple ideas that were proposed. I'm going to discuss our idea. Basically, only about 1,000 rows in 32 gigabyte DRAM need refresh every 250 milliseconds, but we refresh all rows every 264 milliseconds. The key idea of this work is to refresh weak rows more frequently, all other rows less frequently. We didn't want to lose capacity, basically. But of course, there could be other solutions that lose capacity. And that's the idea of this work. So let me talk about the mechanism. The first step in this mechanism, retention-aware intelligent DRAM refresh, is to identify the retention time of all DRAM rows, because you need that, as we discussed, and you need some profiling mechanism for this. At the time, we said you could do it in a DRAM design time or during operation. I believe that is much more important and easy during operation today, like online. And then the memory controller stores rows into bins by retention time. And it uses Bloom filters for efficient and scalable storage. So we're back to the Bloom filters. Hopefully, we will have time to discuss this. If not, we'll do it in the next lecture. But basically, we approximately represent the membership of a row in a bin that says this is the bin of rows that need to be refreshed every 64 milliseconds. So you can have multiple bins. This is the bin of rows that need to be refreshed every 64 milliseconds, and you insert them into the Bloom filter. This is the bin of rows that need to be refreshed every 128 milliseconds, and you insert them into the bin. And this is the bin for everything else. And everything else gets refreshed every 256 milliseconds. In that case, you don't need to represent things, right? Because if you're not in the 64 millisecond bin or 128 millisecond bin, you must be in the 256 millisecond bin according to the design. So basically, it turns out for a 32 gigabyte DRAM memory, you can have very small storage if you design your Bloom filters correctly and nicely. And we will discuss Bloom filters in a little bit more detail, hopefully. And then what happens at runtime, once you form the bins, and you can basically keep populating your bins over time, right? For example, initially, all rows have to be refreshed every 64 milliseconds. Over time, you do some testing. You figure out some rows are very strong. You basically put them into the bin that requires refresh every 256 milliseconds, right? So you can basically move the rows between the bins once you figure out more information. And memory controller refreshes rows in different bins at different rates. Essentially, this amounts to checking the bins to determine the refresh rate of a row. So there's some complexity clearly in the memory controller, but it's not that bad as we show in the work. So let me give you the key takeaways, and then we're going to talk about the challenges. So the hardware cost is not bad. Refresh reduction is actually quite good based on the parameters that we said. It's you reduce refreshes by almost 75%, which is what you would expect from that distribution that I showed you. DRAM energy reduction, dynamic energy reduction is significant. Idle power reduction is also even more significant because when you're idle, most of the time you're just spending your energy on refreshes. And performance improvement is also significant. This depends on what workloads you're executing. This is averaged across many, many workloads. It's 9%. So this is an idea that improves performance as well as energy at the same time while having low hardware cost. And we showed that benefits increase as DRAM scales in density. For example, with 4 gigabit DRAM chips, dynamic energy reduction is 16%, but at 64 gigabit DRAM chips, refresh becomes a bigger problem. So energy reduction is even higher. Performance is like that also, as you can see. With 4 gigabit chips, performance improvement is 9%, but with 64 gigabit chips, performance improvement becomes even higher, a lot higher actually, because DRAM becomes a much bigger bottleneck when you're refreshing a lot more. Okay, I'm not going to go into the details. You can read the paper. And this is a potential reading for your homework assignment also. Okay, and there's more further readings also. But basically, I think this is an example of understanding what's going on at the device level. You can actually solve the problem at the architecture level. Right? Device level, you have some understanding. You have this manufacturing variation. At the architecture level, you design some mechanisms to take advantage of that variation. So I think this is fascinating because you can cross the boundaries of the stack. And also, now you have cooperation between multiple components. The DRAM device has this characteristic. Memory controller figures out these characteristics and enable a much better refresh solution. But let me spend some time on making this work. So there's some wise people who said that good ideas are a dime a dozen. Basically, there are many, many good ideas in the world, but making them work is the real contribution. That's the real difficulty. And this is where Radar actually becomes interesting. So we wrote this paper, Radar, it showed great results, but there were some open questions also. And we clearly, you cannot discuss everything in a single paper. Sometimes reviewers also have the unreasonable expectation that everything has to be done in a single paper. You can never do that. There's no way you can do that. So there has to be some boundary that a paper can cover, and beyond that boundary, it's future work. And that's essentially what we did over here. So we wrote Radar based on our simulation results, and then we decided, now let's take a look at how we actually really build it. So building it requires profiling, as we discussed, right? In the Radar paper, we said that this can be done by writing the data to a row, prevent it from being refreshed, and measure the time before data corruption. Yes, that's the basic idea of profiling, right? If a row fails, for example, after 128 milliseconds, you basically say, oh, this row needs to be refreshed every 64 milliseconds. If a row fails after 256 milliseconds, you say, this row needs to be refreshed every 128 milliseconds. So this is how you determine the bins, right? By profiling. And if a row doesn't fail after 256 milliseconds, you basically refresh it every 256 milliseconds. The question is, of course, what should be your data pattern? How often should you test? And do these characteristics stay stable? And it turns out there are challenges over here. So is it really this easy? And it turns out it's no. And we discovered the difficulty of it by building this infrastructure. That's the reason why we built this infrastructure. We wanted to really make this work. But it turns out there are two major challenges that make it hard. One is data pattern dependence. We've seen this with RowHammer. And the other is variable retention time. Let's go quickly over data pattern dependence in case of refresh. Essentially, the problem is retention time of a DRAM cell depends on the value it has and the values of cells nearby it. So it's retention time is data pattern dependence. And the reason is, when a row is activated, all bit lines are perturbed simultaneously. Let's take a look. So these are the bit lines, as you can see, and these are the word lines. And I showed 3 cells in a row, but you can imagine 8 kilobytes, for example. When you activate the row, which is this row, when you basically apply high voltage to that word line, all bit lines, these are the bit lines over here, get perturbed simultaneously. Because what happens is when you activate the row, this access transistor turns on, and there's charge sharing between the capacitor and the bit line in all of these. And all of these bit lines get perturbed. Now, there's electrical noise on the bit line. And this electrical noise on the bit line affects reliable sensing of the DRAM cell. And the magnitude of that noise is affected by values of the nearby cells, because there's bit line to bit line coupling. So there's coupling between adjacent bit lines. These red bit lines affect the blue bit line. And then there's bit line to word line coupling. This blue bit line gets affected by the red word line. So there's voltage coupling that happens, capacitive coupling that happens between bit lines and bit lines and bit lines and word lines. And retention time of a cell depends on this noise, essentially. Because if this noise is very high, then the leakage path is very fast. And as a result, you can see that the retention times depend on the data patterns stored in nearby cells. And one difficulty is that now you need to find the worst data pattern to find the worst case retention time of a cell, because your data pattern is quite influential on the retention time. If you don't find the worst case retention time, which is dependent on the worst data pattern, then you may actually incorrectly refresh a cell. A data pattern can cause charge leakage, and your cell may not be refreshed. So this makes the problem hard. So the question is, who finds that data pattern? So basically, any retention time profiling mechanism must handle data pattern dependence. Intuitive approach would be this: identify the data pattern that induces the worst case retention time for a particular cell or device. But the difficulty is it's very hard to know at the memory control which bits actually interfere with each other because of the mapping issues that we discussed, right? Logically consecutive bits may not be physically consecutive in DRAM. And remapping, and there's also remapping of faulty bit lines to redundant ones internally within DRAM. The second problem is worst case coupling noise affected by non-obvious second order bitline coupling effects. And this makes the problem very hard, actually. So this is one of the difficulties. Let me give you the other difficulty, and then we'll discuss the solutions in the beginning of tomorrow. And you can think about the problems. I'm just going to give you the problems right now. So the other difficulty is even worse, I would say. Basically, there's a phenomenon called variable retention time, in which retention time of a DRAM cell changes randomly over time. This is quantum-like effects in DRAM. Basically, a cell alternates between multiple retention time states. And the reason, this is actually a well-known phenomenon. It was demonstrated in 1987, but our works demonstrate that this is getting much, much worse in current DRAM chips. So essentially, the problem is there's leakage current in the cell, and that changes sporadically due to a charge trap in the gate oxide of the cell access transistor. So there's a charge trap over here. When that trap becomes occupied with charge, the charge from the capacitor leaks more readily from the transistor's drain, and that leads to a short retention time. So there are some cases that happen randomly. This is called trap-assisted gate-induced drain leakage, or TAGIDL. And this is a random process. Prior works have shown that, and our works also shows that it's a random process. So basically, worst case retention time of a cell depends on a random process, and you need to find the worst case despite this randomness. And this is tough. So let me give you some examples. This is room temperature, very low temperatures. That's why the retention time is very long, as you can see. But even then, you can see it. You do the testing in different hours. You test the retention time. Sometimes the cell retains data for 6.1 seconds. That's the maximum time we tested. Sometimes the retention time drops to 3 seconds or less than 3 seconds, as you can see. So clearly, there's a variable retention time phenomenon going on. This is not due to some other reason. We're testing the same cell with the same data pattern. Nothing else in the environment is changing. Randomly, the retention time is dropping. The temperature is also constant. Okay, and this is an example showing the phenomenon. So this is a collection of all the cells in a 2 GB chip family. And what we're plotting here is the minimum retention time on the x-axis and the maximum retention time on the y-axis, and this is a density plot. The darker the box, more cells fall into that minimum versus maximum retention time xy point. Ideally, if there is no variable retention time, you would expect a cell's minimum retention time to be the same as its maximum retention time, which is a linear curve. You should really expect this red line over here, right? But that's not what we get, as you can see, right? As you can see, most failing cells actually exhibit variable retention time. In fact, many failing cells jump from failing cells mean these are the cells that get a retention failure in all of our in any of our tests. And many failing cells jump from very high retention time to very low retention time. So the variable retention time phenomenon actually quite bad in existing chips. Okay, let me talk about the implications, and then we're going to conclude today. So basically, because of this variable retention time, it turns out there doesn't seem to be a way of determining if a cell exhibits variable retention time without actually observing a cell exhibiting variable retention time, because it's a purely random process as far as we know. That's the difficulty. And this was shown. And the second is variable retention time complicates the retention time profiling by DRAM manufacturers. So somebody can say, okay, this is a DRAM manufacturer's problem. We say no. Why? Because when you expose a chip to very high temperatures, you can induce variable retention time in cells that were not previously susceptible to variable retention time. And this can happen during soldering of DRAM chips. So when you take a DRAM chip and solder it on a board or a DIMM, you basically can change the retention time because you're actually exposing the chip to very high temperatures. And this basically renders potentially manufacturer's retention time profile to be inaccurate. And that's why this becomes a system problem also. So one option for future work that we proposed in this paper that I'm going to mention briefly is to use ECC, error correcting codes, to continuously profile DRAM online while aggressively reducing the refresh rate, what I mentioned earlier. But this requires you to keep the ECC, error correcting code overhead in check. And this is the paper, basically. This is the first paper that we wrote based on the infrastructure that we designed in 2011. It was published in 2013 in ISCA. And we're going to cover some of these things in the next lecture. Since we're already out of time, this is just a foreshadowing. How can we reliably find the retention time of all DRAM cells? And we're going to talk about that tomorrow. But I think right now, since we're already out of time, we should part. If there's a burning question, maybe I'll take it. But you can also ask your question tomorrow, because tomorrow we're going to start with this and hopefully move to memory latency. I hope I'll see you in person tomorrow. We have hopefully an alternative solution to that room if that room is still problematic. Okay, take care and prepare questions for tomorrow. I look forward to them.